think it's a good time to start. Okay. Okay, so I think we can start with this year's edition of the workshop. So good morning, I'm happy to see you all here. I am Andrea Rosà from University of Lugano, and this year I had the pleasure to organize VMIL 2023 together with Martin Hans from National University of Singapore. So welcome to Cascais, and also welcome to the 15th edition of the International Workshop on Virtual Machines and Language Implementations. Before starting with the first session, I just would like to say a few introductory words. The workshop aims at advancing the state-of-the-art on the design and implementation of programming systems with virtual machines as a particular focus. The first edition of the workshop was held in 2007 in Vancouver, at that time together with AUSD, and now we have reached the 15th edition of the workshop since then. Unfortunately, you know that we had several years where COVID-19 somehow lowered significantly the number of submissions, but I'm very happy to say that this year the workshop could attract much more interest than in the past. So today we have a full-day program with 11 accepted papers. We have 8 research papers and 3 short working progress papers. Unfortunately, not all the authors were able to attend at the workshop, so today 3 presentations will be held remotely, but luckily 8 of them will be held in person. And the topic of the accepted submissions this year spans greatly, so today we will hear talk on compilation, both ahead of time and just in time, then interpreters, dispatch, polymorphism, garbage collection, binary code generation, type stability, and also debugging. And the keynote of the workshop will be given by Professor Shigeru Chiba from the University of Tokyo, who will talk about polyglot programming through foreign functional interfaces. And the keynote is scheduled later today at 11 a.m. Before starting, I would like to thank the authors for their submissions and all the program committee members for their hard work and their high-quality reviews. Actually, this year, each paper received 3 reviews, and this means that the reviewing load for the program committee was a bit more than initially expected, because there are 10 people on the committee. So let me thank again all the people in the committee for their extra work. And also, I would like to thank the steering committee for the great support in organizing the conference, and also for moving forward and work for organizing the next edition of the workshop. And finally, thank you to all of you for your participation. I hope that you will enjoy the workshop and the discussion that will arise here in the room, and enjoy VMIL 2023. Thanks. So I would like... So we can now start with the first speaker. There you go. So we can start with the first session of VMIL 2023. The first talk will be given by Duncan Lauder from University of Glasgow, and the talk is titled Cherry, Performance Enhancement for a Bytecode Interpreter.
Thank you. So I'm pleased to present this work, which Digis and Jeremy sitting there, were also a part of. So I present on all our behalf. We have sort of 3 main contributions I'd like to talk about here. The first is our approach to the performance optimization of a Cherry based runtime. The second is a particular experience of the current profiling infrastructure on Cherry systems. And the third is an important observation about performance of Cherry systems in general. So first, what is Cherry or Morello? So Cherry itself stands for Capability Hardware Enhanced Risk Instructions. It's a set of instruction set extensions that allow certain spatial memory safety guarantees to be made in hardware. You can use it two ways, with a hybrid ABI that allows you to use mostly capability oblivious code that uses an implicit capability register to sort of make everything sound under the Cherry framework. And the second, the pure cap ABI, exposes the full features and the full protections, and that's the one we target because we're aiming here to maximize the benefits of security. Morello is a prototype architecture that implements the Cherry extensions on top of the ARM 8.2a instruction set. Specifically ARCH64, we don't deal with ARCH32. Morello capabilities, so capabilities in general are fat pointers that contain privilege information as well. So anytime you make a memory access, you need to have a capability authorizing that access. A capability will have its address, that's just your standard pointer. You can do normal pointer arithmetic on it. The other bits of it are a bit more interesting. You've got bounds, which are the region of addresses over which the capability is valid. If you try to use a capability to authorize an access out with the bounds, it will fail with an architectural trap. You've got permission flags, 18 of them. These include, read, write, execute, as well as some more specialized permissions like being able to read and write other capabilities. You've got an object type field that I'll explain a bit when I come to sealing. And you've got a provenance tag. This is possibly the most important thing. You've got a 1-bit tag stored out of band, so you can't access it directly with any sort of memory instruction that allows you to distinguish a true capability from just a sequence of bytes. So this guarantees that capabilities are properly derived from other capabilities. If you use an invalid chain of derivations to create a capability, the tag will be cleared and you won't be able to use it to authorize anything. Derivations of capabilities are monotonic in bounds and permissions. You cannot widen the bounds or increase the permissions. Permissions are dealt with a bitwise and bounds will throw a trap if you try to widen them. The object type field allows you to seal capabilities to prevent modification until they become unsealed. So this is a bit of a special thing. The most important kind of sealed capabilities are sentries, which are a way of protecting function pointers so that you can't change the address with you can jump to the entry point, but you can't jump to an arbitrary point in the function, which foils return-oriented programming attacks, and you can't read the actual code of the function either without jumping to it. So it's also important to note we have single source provenance. Each capability has to be derived from exactly one other capability. So you can't merge two adjacent capabilities together. That's not allowed in this system. Some implications here. The size of our pointers is longer than the size of our integer words. If you cast a pointer through just a long or other integer type and back to a pointer, you will lose the provenance, you will lose the metadata and the capability tag, and you won't be able to actually use it to dereference. If you cast through the uint pointer t type, that will preserve provenance because that's a type specifically defined to allow you to preserve pointers as you cast them through an integer. A related thing though, because the uint pointer t type then has to actually hold the entire capability, adding to int pointer t types is ambiguous because like I said before, you can only derive a capability from one other capability. And so it doesn't know whether you're adding the address of the second to the first capability or the address of the first to the second capability. So the compiler will complain about that. you have to explicitly throw away the provenance of one of your operands before you can use these binary operators. Next, the maximum representable value for a uint pointer is not what one would expect based on its size of, because the top 64 bits of the uint pointer are reserved for the capability metadata. So the representable range is only that of your 64-bit integer, despite being 128 bits in width in memory. So those are a bunch of bad things, or things that have to be worked around. The last thing is very important and is the big positive, and that's that many undefined behaviors in C that would ordinarily might corrupt arbitrary data or result in leaks of various kinds, or maybe a seg fault, but you can't guarantee that, instead become a predictable capability protection fault that is guaranteed to be thrown if you make an access that's invalid under Cherry. So this is an important protection. So in prior work, we ported the MicroPython interpreter to PureCap. And MicroPython is a bare bones Python interpreter designed mainly for embedded systems, so it's optimized for code size, but it has desktop ports as well. And in yesterday's talk at MPLR, I detailed how we ported the sort of biggest variant of MicroPython to the Cherry BSD on Morello and under the PureCap ABI. And there's a DOI there for anyone who is interested. So next, we get onto the subject of this talk, which is the benchmarks and the performance enhancement that we did on this. So anytime we talk about performance, we've got to specify what benchmarks we're using. So there are 11 benchmarks in the performance bench suite built into MicroPython, so we decided to use those for consistency with MicroPython. I also got to detail our metrics. So of course we track total time because that's the sort of the important execution overhead that we want to see. We also tracked RSS because the idea of having all pointers twice as large, we want to see what the impact in real terms on memory is. We also tracked instructions retired and cache misses in order to help diagnose the source of execution overheads. And lastly, it's important to notice that all the figures that we'll use henceforth will be normalized, so they'll be represented as the ratio of the PureCap build value to the hybrid build value. The PureCap and hybrid builds are run on the same machine, so they should be comparable from a hardware standpoint. So before any optimizations, we had this scary headline figure of 137 times overhead on the Pfannkuch benchmark. And you can see a similarly upsetting overhead in Queens. Both of these, you'll note, also have very high instruction retires. So the CPU is clearly very busy in these. So our symptoms, both our benchmarks that were worst off involved repetitive list slicing operations, which is interesting. And list slicing in Python requires actually allocating and then quickly deallocating a whole bunch of heap objects. Using PMC stat, which is the BSD sort of equivalent of perf, and sampling every 2 to 16 instructions, we found that 99.3% of our samples landed in the allocator. So that quickly tells us the sort of general situation. As a side note, it was difficult to use PMC stat because the built-in PMC stat way of translating raw addresses into what symbols they relate to doesn't actually work on PureCap. So I had to write a bit of an external script to be, translating them for me from an extracted symbol table. The vast majority of these samples within GCLIC were in a loop that searches for a contiguous set of free blocks long enough to hold the allocation. And we also noted in the statistics when we told it to dump GC data that we had far fewer one-block allocations on PureCap than on Hybrid. So Hybrid had a few thousand one-block allocations, far more than any other block count. PureCap had only 12 of them, and there were far more two-block allocations. So you might see where this is going. The doubling of pointer sizes has caused, with no change in the block size, has caused allocations that would ordinarily be smaller to take up more blocks, to take up 2-3 blocks. And because of that, we're dealing with memory fragmentation. It turns out the MicroPython allocator, it's designed to run very lean in its sort of home state. But if you don't have a lot of one-block allocations, it will quickly become very fragmented and have huge performance hits based on that. So the fix here was to change the default block size from being based on the size of an integer, which is, of course, the same on Hybrid and PureCap, despite the pointers doubling, to one based on the pointer size. MP-Object-T is the sort of standard type for MicroPython objects that is a low-bit tagged union of either a pointer or an unboxed integer or intern string identifier. So after doing that fix, you'll notice we no longer have any 3-digit overheads, which is nice. In fact, the benchmark that we were worrying about earlier is down to 1.7 times. It's no longer our biggest culprit. We now have to worry about Pystone, which has nearly a 4 times overhead. And the fix turned out to be actually quite similar. So if we look at flame graphs, which basically show the samples over time from the PMC stat, so you can see the entire stack trace. And it's not linear time. It's not like it goes right to left. They're merged so you can see how much of the time is taken up in each function. And you'll notice I've outlined in red the GCAlloc calls. So again, while it's not 99% now, we're winding up with a significant amount more time in the allocator on PureCap than on Hybrid. It barely visible on Hybrid, but PureCap is quite significant. Also, the most expensive calls to GCAlloc came from this fun BC call. So we examined that function in particular. We also instrumented the GC, and it turns out there are 200 times as many of those free block search loops on PureCap as on Hybrid. So clearly, again, stalling there. We also noticed that there were thousands of 3- and 4-block allocations that appeared in PureCap that didn't appear in Hybrid. But unlike the previous issue, these weren't allocations that had previously been smaller on Hybrid and are larger on PureCap. They didn't exist at all on PureCap. So this was a bit confusing until we realized that the fun BC call, the only place that function directly calls the allocator is when it wants to spill a call frame to the heap. So by default, only frames no more than 16 integer words in size get stored on the stack. Anything else gets allocated on the heap. And so, again, because this is based on an integer word, when we switch to PureCap and the size of the call frame has a lot of pointers in it, so that's going to increase significantly while the maximum size on stack hasn't changed. So we're going to wind up with a lot more spills. And in particular, the 3 and 4 bytes, 3 and 4 block allocations correspond to the exact set of sizes that can be allocated on stack in hybrid, but once you double them, wind up being heap allocated. So the solution here was to base the threshold for spilling on pointer size as well. So you'll notice in both of these two things that the issue is fix an assumption about pointer size being equal to integer size that was assumed in optimization earlier, and that allows the optimizations to sort of be compatible. After this, you'll notice we dropped by about 1/4 there, so we're at 2.8 times. Still too high, but you'll notice that we're getting more and more sort of not CPU busy, or not instructions retired at least. So we're getting to the point where it's going to be a bit more difficult to optimize because we're not just spinning. At this point, the side-by-side flame graphs didn't tell us much because they were too similar looking. There wasn't enough visible difference. So we use this sort of difference flame graph where the color indicates the overhead of pure cap relative to hybrid. More red is more overhead. And you can see here that now the execute bytecode method there it accounts for both of the two reddest areas. So that's our VM loop. That interprets the bytecodes that we've compiled down to. It uses a table of computed gotos to make a very tight loop. And for some bytecodes, an iteration of this loop, a processing of the bytecode, including the goto, is 11 instructions. So any sort of slowdown there winds up getting magnified significantly. What we found out that this actually was inadequate LLVM optimization. So there are several places where LLVM, when compiling on PureCap, knows that it can optimize things down, and that when inspecting disassembly, know that these instructions are superfluous. You could just use one instruction where you used 3. But because the LLVM PureCap compiler doesn't yet know that is true for capability-based things, it's generated longer binary code than it needs to. So a couple examples. Whenever we had to load a small constant uint pointer, which it appears as capability, it was compiled down to 2 instructions to load that rather than 1. When we wanted to cast an integer without provenance to a uint pointer t, that took 2 instructions, where by default, if you've moved an untagged integer into a register, it will clear all the top, all the capability bits, and so you don't actually need any instructions to cast whatsoever. And then it took 3 instructions rather than just 1 to compare a uint pointer t against a constant. Now, compares of capabilities are done only on the addresses, so you could just do a single instruction for an address compare, but instead it loads that constant as a uint pointer t using 2 instructions, and then performs a compare on the integer parts, which is just unnecessary. So it wasn't, fixing this directly would have required delving into the LLVM backend and was a bit out of scope for this project. But what we did to prove that this was a real overhead was we went in and patched the binary so that we could see the changes of at least some of these optimizations. We didn't patch every, just a few patches in the execute bytecode. And you can see that created another drop by 1/3 in normalized total time. So this is after our 3 sort of quick optimizations. Not very sophisticated at all at this point. And we've now got everything down to between 1.5 and 2 times execution with a geomean of 1.7. You also notice instructions retired is quite low there too. That winds up at a geomean of 16% overhead. And most of the sort of higher bars are the caches. So what do we take away from all this? First off, the PureCap Cherry port can have a significantly different performance than the legacy code if it's just naively ported. Anytime you're porting Cherry code, there's been a lot of focus on needing to fix assumptions made around functional requirements of the code, but the assumptions made when creating non-functional requirements, equally important. Porting efforts should pay attention to assumptions made when optimizing the code, not just when making it correct. Otherwise, you wind up with these 100 times overheads that no one likes. The good news is it's actually fairly quick to fix these sort of assumptions in a lot of cases, because it'll be, one define or one, constant somewhere that needs to be tweaked, and then suddenly everything's better. The last thing is that the headline figure, 70% overhead, shouldn't be discouraging. So we've got further optimizations potentially available at the source level. We haven't looked into, for instance, removing redundant bounds checks because Cherry does hardware bounds checks, so their software bounds checks can probably be removed. Using the tags built into the capabilities to make more efficient the distinction between a pointer to an object structure or an unboxed value. Various things like this that can be changed at the source level. The second is that the Clang LLVM optimizations are improving as the toolchain for PureCap matures. So it is fairly recent, and the optimizations are being worked on. And the last is that the hardware is going to improve. So the report out of Cambridge that's fairly recent on the performance of Morello suggests there will be significant future improvement. There are currently bottlenecks, for instance, in the branch predictor if you're using branch to capability instructions. And well, guess what? The tight loop that I was talking about with a computed goto, on PureCap, that winds up being a branch to capability. So given that we only saw a 16% overhead in instructions retired here, it seems fairly likely that improved hardware can reduce the overhead in execution time significantly, which agrees with what Cambridge was saying about this. So that's all from me, and yeah.
So thank you very much for your talk. Is there any question?
So you sort of alluded to it. Can you use the object tags as user code to indicate like type tagging in a dynamic language system?
Mm. Yeah. So you're talking about the capability tags, right?
Yeah.
The provenance tag. Yeah. So they have the architectural duty, right, of distinguishing a valid capability from something that's not a capability. So you can use it if you've got something that can either be a pointer or not a pointer. You can distinguish based on that object tag. It doesn't get you more fine-grained than that, but it can get you that. The one thing you do have to worry about if you're doing that is if you do certain invalid manipulations on a capability, it will clear the tag on the capability. So you've got to be careful that you're not having a situation where a capability with a cleared tag winds up getting misinterpreted as an object of a different type and causing weird behavior that you don't expect.
And that seems good, but.
Any other question?
So have you applied source code optimization to MicroPython? Because at the end you mentioned that the advantage of using Morello is you can optimize, check type tag checking and etc. So have you, is that
Yeah, so I mean, well, that's something we definitely plan to do going forward. At this point, we were really just looking at the way you can bring the overhead that you've gotten by porting it down. So trying to sort of mitigate the sources of overhead rather than direct improvements based on what we have now. But that is definitely sort of the next step. And like I said, that is likely a fruitful area.
Any more questions?
Do you know where the rest of the 16% is coming from? Is that mostly constructing capabilities, or is it additional wider compares that you need, or?
Yeah, so I mean, it comes from a few places. You've got situations when you take the address of something on the stack, for instance, the compiler automatically inserts instructions to give it proper bounds, so that you're not, if you then pass that to somewhere else, you're not allowing access to the entire stack. Similarly, in the heap allocator, there will be a place that narrows the bounds before it returns, and then in a reallocate free, a place that rederives the wider bounds from an existing sort of whole heap capability that it maintains. So you've got a few places where you've got to add extra code just innately. It probably could be brought down further, to be honest. This isn't a comprehensive treatise on all possible sources of overhead. This is just showing sort of the biggest ones that can just be knocked out very simply if you know what you're looking for.
Thanks.
I think we have time for another question, if there is any. Yeah, maybe a quick one.
So what is instructions retired? I'm not familiar with the term. Could you explain it in very short?
Okay, so yeah, so it's just the number of instructions that the CPU has actually completed for working on the benchmark. So, just count each time an instruction is executed and fully completes. That retired means, it's not speculatively executed or partially complete. It actually completes fully. Then you increment instructions retired.
Thank you very much for your talk. The second talk of the session will be given by Dave Mason from Toronto Metropolitan University. And the title of the talk is Revisiting Dynamic Dispatch for Modern Architecture.
Sorry, I just realized I need to mirror my displays. That. Sorry, I didn't check this correctly the first time. There we go. Okay. Sorry about that delay. Okay, so this talk is about revisiting dynamic display. So dynamic languages remain important 50 years on. JavaScript, Python, R, Ruby, all pretty big players. Smalltalk, Scheme, Groovy, a little bit less so, but still, some of us like to think important. But commodity computers have changed dramatically, and they have larger memories, multiple cores, but those aren't necessarily being taken into account, and the problem sets are growing ever larger. So I'm building a new Smalltalk system called Zag Smalltalk. It's a from scratch implementation. The low level is implemented in a language called Zig, which is a modern C replacement, and it's quite an interesting language. And one of the primary goals here is to support multi-core from the first principles. And the goal is to support existing open Smalltalk systems, because I don't want to rewrite all the user-land code, nor do I have enough grad students to do that. So the motivation for revisiting dynamic dispatch was originally about multi-core execution. The go-to solution for performance in Smalltalk and JavaScript, as it turns out, is inline caching. And inline caching gets complicated if you're looking at multi-core, because you obviously don't want to put locks around dispatch, given how common it is, but it's going to be difficult to do updates appropriately otherwise. But as it turns out, the approach that I've taken also enables aggressive inlining, which is useful, and it also enables better hashing. So I'm going to take a step back and talk about dispatch. I presume many of you, or most of you, get this, but I'll go over it quickly anyway. So, excuse me. Smalltalk message dispatch basically starts off with, we have some target we're going to send a message to, and so we set target to the class of that object, or a superclass if it's a supersend. Then we set current to target, and then we look in the up the selector symbol in currents method dictionary. If it matches, it's great. It's the address of the method code, so we call it. If not, and current has a superclass, then we replace current with the superclass and loop back and do it again. If we get to the end, to the class that doesn't have any superclass, then we, in Smalltalk, create a message object and encapsulate the send, and then we go back through the whole process again, back to target, and set current to target and loop through. And this time we're guaranteed that we will actually find something, because object implements does not understand, and so we'll sooner or later hit that and we'll dispatch. So this is semantically what has to happen, but obviously we'd like not to go through all of this silliness when we're actually doing a dispatch. So the semantics are very clear, but the execution performance is terrible, because I'm not sure how many people are familiar with Smalltalk, but in Smalltalk there are no control structures. Everything is a message send. So that means even if then else doesn't exist, it's a message called if true, if false, and it gets sent to an object, and if every conditional has to be a message send, and we have to go through this process that we just described, that's going to be expensive. So there are three mechanisms that are used in production Smalltalk systems to ameliorate this. First of all, the compiler recognizes things like if true or false and says, oh, I know that this is going to be really an if then else, so I'll turn it into an if then else in the bytecode that I generate. This is an extremely important optimization, obviously, but it's tricky. So until very recently, what most Smalltalk systems did was, if you send the if true or false message to something that isn't binary, isn't a Boolean, then you got an error or message sent to the object saying, must be Boolean. And basically it was told, I need you to give me a Boolean value. And so the object would have to create a Boolean value to return, but it had to do it at the right place. So it actually had to look at the current activation record in Smalltalk that's called this context, had to look at the caller, had to bump the program counter back, and then it could return the Boolean value and things would proceed as hoped for. In more recent Pharo systems, which Pharo is one of the open source Smalltalk systems, what it does instead is when it finds you sent this to something that wasn't a Boolean, it decompiles the method and recompiles it with it as an actual message send instead. Interestingly enough, this was broken. And so there was a Heisenberg bug that only when you happened to hit this situation and it decompiled it, it actually did it wrong. And so your code didn't work. Anyway, so it's tricky to do this, but it obviously can be done. So that's because you want the semantics to work. So I discovered how you had to go about doing this because I created a project a long time ago where I had a maybe value that I needed to calculate the true or falseness of it based on some other parameters. And so I wanted it to actually work. And Smalltalk made it actually work. I just had to jump through some hoops to make it, to get it there. Anyway, so this is the first optimization, and it's obviously critical. The second is there's a global method cache. So it basically caches on the class and selector. This is a global cache. And this gets a 20 to 30% improvement. If we didn't find it, then the target method is searched for using the process on the previous slide, and then the resulting address is cached in an inline cache. So the next time we do the lookup, we just basically go directly to the code, again passing the class plus selector, and that code may say, no, that's the wrong case, in which case it does something more complicated. So about 90% of dynamic call sites or dynamic calls will have a single receiver class, so that's a huge win. And if they don't, there's, most Smalltalk systems have a sort of in-between, what they call polymorphic case with up to about 6 or 8, and it handles those. And if it's not that, then it goes to a more general megamorphic system. And Elliot Miranda claims that most of the dispatch overhead is actually in that 1% of the cases that fall into the megamorphic case. So anyway, this all works reasonably well, but not as well as anybody would like. So let me contrast this with Java dispatch. So Java has invoke virtual, which does the same dispatch, same semantics as Smalltalk. The difference here is because it's a statically typed language, the Java compiler knows the index into the dispatch table that each method call will give. And so it can just do that directly. And the dispatch table for each class has a prefix of the V table from its superclass. And overridden classes replace the ones in the prefix. Since the names of all legal receivers or methods are known, we can just directly, we know where in this V table it is, and we can go there directly. In theory, you could do this for Smalltalk, but there are a bunch of reasons why you wouldn't want to. The simplest one is in Java, object has 10 methods. And so every object in Java has a V table that starts with a copy of the object table. But in a typical Smalltalk system, object has 400, 500 methods. So every single dispatch table would have a prefix of 500 entries. So obviously that's not very viable. And of course, we also don't know exactly what all the possible selectors are. And there are about 100,000 different symbols in a typical Smalltalk image these days. So it's because it's extremely difficult. So we can't do this. So what I've proposed is a flat dispatch where we have a single level of hashing for method dispatch. So each class dispatch table has an entry for every method that has actually been sent to this class, regardless of where it is in the hierarchy. So if it's in object, it still gets compiled into the dispatch table for here, and I'll talk about a bit more detail later. So as implemented in ZAG, what this does is it extracts the class number from the target object, indexes into a static table of dispatch tables, calculates a hash value from the message, and then it indexes into the array of code pointers and calls whatever's there. It passes additionally a pointer word that's in the dispatch table and the selector. So there are three possibilities. One is that this is an actual method, so it points to the method that was compiled for this class, and in that case it just verifies that the selector matches the expected one, because if not, it means that a different selector has hashed to the same value and we need to disambiguate it. So we go and handle that in that case. If this was a position that corresponded to an unassigned hash value, in other words, there was no method, then we go directly to that same code. And the other possibility is that this is a clash or collision on the hashing, and so we go to a disambiguator. In any case, we just basically pull out the pointer and the other value, and then we dispatch. So if a dispatch described goes to the not found code, it simply means there's no compiled method for this class. That doesn't mean there isn't a method that could be there. So what we do is we look in the current class for the source of the method, which we store as an AST. If it's not found, we try the superclass and go on up, just like the Smalltalk semantics does. When we find a method, though, we do something very different, which is we compile that method for this class. So whatever the target class was, we compile that method wherever we found it in the hierarchy for this class. And that means we know a lot more about it when we're compiling it. And we store these as ASTs, so this compilation is very fast if we're just generating simple code. And if we don't find it, then we generate a does not understand, and we do exactly the same thing as before. So the code pointers in the array are actually a pair. So they have a function pointer and a threaded word pointer. The load of the threaded word pointer is not on the critical path, however, because we load the function pointer, and then we load the other pointer, and then we do the dispatch. But it doesn't matter if the CPU takes a while before it loads that other pointer, because we don't need it right away. So there's no extra cost to the execution path over a standard vtable. In the case of a collision, the function pointer is a disambiguator, and the threaded word pointer points to a pair of code pointers, and then the disambiguator basically tests a particular bit number to see which of those it is, and then goes to whichever of those two code points. And then if we have, that could also be a disambiguator, because it doesn't know, it just goes there just the same as the original dispatch did, but will limit the depth that we go to these disambiguators, and if it's beyond a couple, then we rehash it to a larger hash table, which will presumably remove some of those conflicts. So the nice thing about this is that when we're generating the code, we know exactly which class this is going into. So this allows us to do very aggressive inlining. Any message to self is obvious. We go through the same process. We can inline the code. And we also, similarly for super, we know exactly where that code is, and it compiles into the appropriate place. Or sorry, inlines into the appropriate place. Methods with small numbers of implementations, like if true, if false. There's only 2 in the system, so we say, okay, well, then we'll inline those, and we'll do a class dispatch code. So this does the same thing as the compiler-driven one that Smalltalk systems use, except that it doesn't care about the particular selector that we're talking about. It just generates the right code. And then, of course, if true, if false. In the if true case, it asks the block that gets sent, asks it for its value, which evaluates it. But when we inline that code from, from the true class and from the false class. When we send the message to the block, it's now a literal block, and so the block goes away. And so we get exactly the same kind of code as we would have gotten the other way, except in a generalized way. This prevents creation of many blocks, and it also provides a large compilation unit. One of the challenges with languages like Smalltalk is people typically write very small methods, and if you're dispatching all over the place, that's really expensive. It doesn't give the compiler, an optimizer, much room to figure out how it could optimize. So this allows much larger compilation units to allow for optimization. Code generation, I'm not going to talk in any great detail about this, but it supports basically two different models. One is a threaded execution model, and the other is a continuation passing model, described in the paper at the bottom. And it generates whichever of these we want. So the idea is that it can actually generate the threaded code implementation first, which is significantly faster than a bytecode implementation. And then after a few iterations, it can JIT it or something like that. So conclusions, flat dispatch was originally done for multi-core support, but it turns out to have some other synergistic effects. If anybody's interested in looking at the code or contributing or anything like that, it's on GitHub. So questions? And to flip this around. So I'm actually chair of the computer science department at Toronto Metropolitan University, and we have about a dozen faculty positions available right now. I would love for one or more of those to be a programming languages person. So if anybody is looking for a faculty position, there's my email address. Questions?
So you mentioned that inline caching doesn't play nicely with multi-core, but I'm not sure I understand how you don't have the same sorts of, I need to lock a table to insert something into it, problems here that you would have as you with inline caching.
So two things. One is to just replace the entry that maybe goes to an error or whatever with compiled code. I can do a compare and swap, so I don't have to delay for that. I mean, it might be a tight loop, but it's not locked, and that only happens when I've actually hit a does not understand. So it's not something I have to check on every dispatch. I just dispatch to wherever it goes. And in theory, what might happen is I have two cores that are both compiling this method, and then one of them succeeds in replacing it. But that's not a problem. Or in fact, they might both replace it, and that's fine. They both replaced it with the same code. But.
Okay. I think there's probably a version of inline caching that can use the same trick, but maybe not like
Possibly.
traditional inline caching.
I haven't thought hard about that. It's possible that you can do some of that, but given the complexity of the inline caching system, that may be very difficult to achieve.
Yeah, I have one comment and a question. So my comment is that I think Java interface invocation is using similar techniques like flat, dispatching. So it might be nice to compare it with Java's invoke interface. But so that's a comment.
Okay.
And my question is, I understand that the Smalltalk is a very dynamic language. So technically, you can change the method in the class and a class object class.
Yep.
So in that case, what happens? Because your optimization sounds very static.
So I just invalidate,
Ah.
and the next time a dispatch happens, it'll hit the new code.
So you mean you throw all the inline, all the compiled code
Well,
for
I
the
keep track of which methods use this code, and if I replace this code, then I will invalidate all those methods.
Okay.
Any other question?
Thank you for your talk. This context, how do you make sure that in the debugger you actually can observe, or in any program code, the eliminated blocks? Do you have any mechanisms to kind of
No.
restore them?
No, I'm assuming,
Nobody does it. Yeah.
I'm assuming that if you want to do that, you would rerun your code with inlining turned off or something like that.
All right.
Any other question? Okay, then let's thank the speaker again. Okay, so it's now time for the third talk of the session. We will now hear a presentation on a work in progress paper. The talk will be given by Daniel Pekarek from JKU Linz, and the talk is titled Extraction of Virtual Machine Execution Traces.
So, I am Daniel Pekarek, and I will talk about a debugging technique. Imagine you are developing a virtual machine or an interpreter, and it kind of works already because you can run small programs, but if you run something bigger, you run into problems, something crashes, it doesn't really work as intended. Now the question is, how do you debug this? Because, as I said already, it's already a bigger program. So your first idea might be, let's single step through this in a traditional debugger, but this won't really work because you might have to step through hundreds of thousands of virtual machine instructions, and you don't even know what you're looking for, so you cannot set breakpoints either. So this is definitely not going to work. What would be very useful, though, if you could debug the guest code and simultaneously debug the virtual machine code, because then you could step through the guest program until you find the fishy behavior, and once you found the suspicious behavior in the guest program, you could then continue debugging the virtual machine from there on, because now you know where something interesting happens. And this is precisely what we implemented here. But we went one step further. We used an execution trace-based system, because once you used a time travel debugger, you never want to go back to traditional debuggers. And we use the trace view system. It's an architecture agnostic execution trace-based analysis system. And the idea is you record the execution trace of your virtual machine. There are many different ways how to do this. I won't go into detail, but the point is, once you have an execution trace file, you load it into trace view. And then there is an architecture module. It decodes the individual events from the execution trace file, transforms them into an architecture agnostic representation, and then there is a bunch of analysis algorithms which derive new information, like, for example, the current memory contents for any point in time, and so on. And this generates internal data structures, which you can then inspect from a user interface. And our technique is essentially a new analysis algorithm. So we consume the stream of events, we transform them, and essentially we derive an execution trace of the guest program. And then we put that into a new instance of trace view, which again applies analysis algorithms and so on. And since we derived one execution trace from the other, we can also link the events. So when we navigate through the guest execution trace, we automatically navigate through the virtual machine's execution trace too. What does this look like? Essentially like a debugger, with the main difference we can navigate through the program run in any way we like, and we see an actual execution trace instead of the program code as it's stored in memory. I won't go into more detail. You can play around with this. The code is open source anyway. But the question is, how does our transformation work? First of all, we inspect all the events from the execution trace. Question is, which events do exist anyway? For example, memory accesses. Whenever the program accesses a memory location, this is an event. Or whenever the program executes an instruction, it's also an event. And essentially, we inspect those events and check if there is something interesting going on. And if we find an interesting event for our transformation, we can collect data over time, because maybe we have to see more than one event. And once we have collected all the necessary data, we can create a new event, which then is an event from the guest program's execution trace. So essentially, it's like virtually instrumenting our program in an offline way. And what does this look like in practice? Let's imagine we have a very, very, very simple virtual machine. Initially, we'll allocate some memory for the guest program. We load some program code, and then we single step through the program in a while true loop. And single stepping means we load an instruction word from memory and decode and execute it. So our first transformation rule, like virtually inspecting the program, is we will look at this malloc instruction because it allocates the guest program's essentially heap. And we will just remember the address of this memory region. We will need it later. Then the second rule we will need is whenever the instruction is executed, we will generate an event in the guest program's execution trace. And this will probably contain the instruction word, probably also the program counter and other architectural state. And the final rule we also need, whenever we see a memory access and it falls within the region of the guest program's memory, then we will also keep it, otherwise we will discard this memory event. And this is where we need the value we stored in step 1 to figure out if it's a memory part of the guest program. And essentially these three rules are then used to filter the execution trace of the virtual machine, and I hope you can see how this will eventually result in an execution trace of the guest program. Of course, there are many limitations now. What if we have compiler optimizations like inlining or loop unrolling and so on, which would make it a lot harder to write a rule which inspects an event from a certain source code location of our virtual machine. Luckily, we developed the virtual machine ourselves, so we can just disable this if necessary, if it makes problems for us. Second problem, we have this fancy way to distinguish guest memory from the virtual machine memory. But what if there is no such distinction in the virtual machine anyway, like for example in CPython, where everything is just in a virtual machine heap? Well, then we can just pretend we have just one memory area. We don't get the nice separation, but the approach still works. We just get less information in the end. Bigger problem if we have a just-in-time compiler, we get machine code. We don't have nice bytecode or IR. So we don't get a nice high-level execution trace anymore from the guest program, but it's still useful because we can still separate this and purely look at the guest program code, so we don't have to step through a lot of virtual machine code. And finally, what if we have some complex intermediate representation, like for example a GRAL, like in an graph, like in an AST, for example? Then writing rules is still a lot harder. We can still do it, of course. But yeah, it's just more work. And future work, I didn't mention it so far. Right now, the implementation, or for the implementation, you have to manually derive addresses and register names and so on. Would be very useful to just use debug information so we can symbolically resolve source level variables from our virtual machine. It's just not implemented so far because it's a lot of work to do that. This would also give us high level source level debugging for the virtual machine in the end. Another future work piece is right now the trace tool is purely intended for register machines because it was originally developed to debug low-level interpreters, but a lot of programming language virtual machines use stack machines internally, and it would be very useful to have a direct support for this in the system. And finally, this approach also applies to actual hardware because you can simulate your virtual CPU, RTL simulation, and you would get a simulation trace, and a very similar approach would apply there too. And yeah, that's it from my side. Questions?
Any question?
Hello, thank you for your talk. I'd like to ask you about the kind of rules. You put up 2 or 3 rules there at the start that you're going to impose on your system. Are those rules all to be designed by an expert, or could you imagine a machine learning system somehow synthesizing rules for you to make interesting analyses?
The problem is you have to know what you're looking or what you want to look at because you probably developed your virtual machine and you know what it means to execute an instruction in the system. So I guess you will have to write this somehow yourself. But in practice, if it's a bytecode interpreter, this is usually very simple to write.
Okay. Could you imagine a sort of templated library of rules that you could pick from if you were using this system with a fairly standard interpreter, or does that not make sense?
I mean, right now it's kind of like this anyway.
Okay.
But in the end, in the paper I described a PowerPC interpreter, a very simple one with transformation rules, and I think there was no rule longer than a few lines of code, so I'm not sure if you really need templates for this.
Okay. Thank you.
Any other question?
Thank you. I'm wondering if you could give an idea as to the latency and the overall user experience and the user interface once you add extra work of processing the trace events?
Once all the data is loaded into the tool, it's extremely fast because there is a big limitation right now. Everything is loaded in memory. The real limitation is you need a rather short trace or a lot of memory to process it.
I see. Thank
But
you.
other than that, it's almost instantaneous navigation through the trace.
Very nice.
Could you give us a coarse idea of how large your trace files get or how fast they get large?
Depends on the program you trace, of course, but they get very large, very big, because one problem here, or idea here was, it's a complete execution trace with all instructions that were executed and all memory access and so on, because you want to debug the virtual machine itself. And there are other ways how to debug this too, so the system itself does not apply some fancy compression and so on. And essentially, I think 60 million instructions is something like 4 gigabytes of execution trace, and you need something like 32 gigabytes for analysis then. So it's extremely large.
16 million CPU instructions.
Yeah, exactly.
Okay, that's quite much memory that you need.
So it seems generally like you talked here about an offline debugging where you take a trace and then process it. Would it be possible to use similar principles for a debugger that steps through the program as it's running, you know, and potentially save memory that way, or is that not possible for some reason?
Also possible, we just didn't do it. And essentially what we do here is kind of like dynamic instrumentation anyway, but we do it offline. You could do that too, but yeah, we just didn't do it.
Any other question?
Thank you. You said this is open source, but when I look on GitHub, I see other TraceView things, but I don't, under your ID, but I don't see TraceView itself.
It's linked in the paper.
Okay.
At the end of the paper.
Any other question? Then I think we can take the speaker one more time. So it is now time for the last talk of the session. This will be a remote talk, and I think it will be given by Marcel, right? Tom, okay, sorry, Tom Brown, can you hear us? So, Tom, can you hear us? Or, yeah, you should unmute yourself. So Tom, if you can hear us, you should unmute yourself. I will try also to write you. That's me. That's me. That's me.
Okay, I can speak now.
Yeah, okay,
I guess I should start.
Okay, so it was me trying to connect to the channel because you were muted.
I don't know.
Okay.
Don't we have all microphones ourselves turned off? If you move them out, I think we can hear us.
Again, sorry?
When you move the mouse around, our Zoom microphone was turned off.
I see, okay, I see. So should be now all good? Yeah. So Tom, can you hear us? No. Yeah. The problem is that if I join, it would be. So you are yeah, that would be great. So, but he will not hear.
Okay, quite interesting communication here. I'm not muted.
We are muted.
Okay. Okay, welcome to my presentation, transpiling slang methods to C functions. Let's start with the challenge. The challenge was mapping a source language, in our case slang, which is a subset of Smalltalk, to another language with different language capabilities, which is C in our case. And the big challenge is that slang supports polymorphism and C does not. And our goals were extending the use of polymorphism to static polymorphism. So polymorphism that is determined at compile time, no dynamic dispatching at runtime. And we didn't want to do a big rewrite of the translation tool because this is just a sub-part of implementing a new garbage collector. So it wasn't the main challenge. Yes. What is our context? Our context is the Open Smalltalk VM, which is a VM for Smalltalk dialects like Greek. And now the room is unmuted. I can hear you. And the advantage of writing the VM in slang, a subset of Smalltalk, is you can execute it in Smalltalk. So you can use the powerful Smalltalk tooling, the debugging, the type feedback loop. That's really nice. And so the workflow is developing the VM as long as possible in Smalltalk until it's too slow.
Tom, sorry, can you hear us?
Yes, I can hear
sorry.
you now.
Oh, finally. So we had some technical problem in the room. So what happened is that you were not hear us. And at the beginning, when you were presenting, the audience could not see your slides. So I'm so sorry about that. Do you mind if we start over? Because this time everybody can see your slides, and so we can, and also I can properly introduce you. I'm sorry about that.
Oh, okay.
Okay.
Then, well, do it and say when I should start.
So, yeah, so I'm so sorry for the technical issues. So we are now, it's now time for the final talk of the session. The talk will be given by Tom Brown. And the talk is titled Transpiling Slang Methods to C functions, an example of static polymorphism for Smalltalk VM objects. This is also a work in progress paper. So Tom, when you like, please go ahead.
Okay, again, welcome to my talk. As I said, the challenge is mapping a subset of Smalltalk slang to C, and we want to have some reduced set of polymorphism, static polymorphism, which is polymorphism you have at compile time, no dynamic dispatches, and we don't want a big rewrite of the translation tool. And the whole thing is done in the Open Smalltalk frame, which is implemented in Slang, so you can execute it, you can debug it in Smalltalk, which is quite nice. And so you want to stay as long as possible there, and afterwards you compile it. Here's an example of a slang function. It's just an example, so let's be here too long. You have pragmas that are method annotations where you say something like the C return type should be that and that. You could say, please inline the function for me, and such stuff. And there are, you write normal Smalltalk code. Sometimes you have such things. You want to say, I don't want to do anything in C, or I just want to do something in C. In Smalltalk, don't do it. So we have capabilities for that too. And what I did in the past was writing a second garbage collector. And I did this in the simulator. As I said, it's quite nice to work there. And I stayed there. I'm more of a high-level programmer, more a Smalltalk programmer, so I use strategy pattern, and that's quite nice if you just work in the garbage collector, just work in the simulator. But in the end, I needed both garbage collectors in the VM, and that's nothing that's supported by. That's interesting. By Slang until then. So we needed some extension of the Slang translation. Oh. It's quite interesting at the moment. Okay, so the first try was direct static polymorphism. That's just prefixing the methods. So we have the complete marker, the incremental marker, and say, okay, we prefix these methods. And in the source code, you have configuration. So you say all calls to the receiver marker should be resolved to the incremental marker. And the internals will that's quite annoying. We'll resolve this to the corresponding function. But this approach isn't enough. If you have a configuration with the default marker to incremental marker set, as an example, on the comp marker for complete marker, and you call it, so you will call the CM mark, and if CM mark my display doesn't refresh at this moment. It's interesting. I don't know if you can see it or what you can see. Can you see us? No. You have the memory manager in this function.
So we can see the slides, and to us they are advancing without any problem.
Oh, for me, they sometimes freeze and don't advance. That's a bit annoying. If we have the complete marker and we call something else that isn't touched by the polymorphism, it will, when it resolves the next operation on the marker, it will get just a marker call, because the com marker is just an exception. We want normally the marker, and we will call the incremental marker operation, which is mostly not compatible with the other logic, so that's a problem. So we need another approach, and that's the spreading approach. And in this approach, we have a configuration again for the marker as an incremental marker and the complete marker. We say these are the possibilities and what is the default incremental marker. And logically, what will happen is we get 3 versions. We get a store version, that's the default, so incremental marker, and the prefixed versions. All calls going out of them are resolved to complete marker or incremental marker in these cases. So this is something we apply to existing code base. So we want to do it easily. So we did some works on economics, and calls from polymorphic classes like the complete marker generally resolve to calls resolved for this class. So the complete marker will call functions, and they will resolve to the complete marker version. We can associate classes with polymorphic classes. Some classes are written in mind with only working with the complete or the incremental logic, so we can associate them. And then there's some fine-grained control we can do on method receiver based on the whole function. Again, it's not refreshing yet. No. Okay, we take the example from earlier again, now with a spreading polymorphism logic, and again the com marker for complete marker. We call the com marker with mark. It will it will again call an operation on the memory manager, and because we are in the complete marker, it will resolve to the CM version of the call. And now because everything here is resolved for the complete marker, we get the CM mark operation, which is what we want. So solved. Now a short experience report. It worked quite nice in the end, but at starting time, already slang is a bit finicky to work with. Sometimes it just doesn't translate, or you have problems like it doesn't generate all methods you need to see. So it's then that's debugging it. It's quite annoying. What my tooling introduced is that you get prefixes for the C functions, which can be a bit annoying if you're in C debugger and you assume there's a function that's called without the prefix. That's a minor inconvenience. What's a bit more difficult, and that's more of an implementation thing, is the information how to resolve a method is spread from method to method. So if you go to a method that isn't influenced by polymorphism, and you call something that's influenced by polymorphism, you go back to the default case. So that will breach the information spreading, so you can get invalid state again, like for the direct for the first case, for the direct approach, and then you have to go in and find it and annotate some methods as you need it. One thing I did what was a bit helpful was exporting a call graph of the VM, which is possible because he doesn't have you can see it and see what method is called, and that's unique. And I annotated it with meta information, so we can ask it something like, show me where we resolved something for the incremental garbage collector and where it goes through a call chain, and how we come to the stops the world garbage collector logic, and then we can validate, is it okay, is it not, and possibly annotate some methods. Future work is generally more Slang improvements, but explainability, as I said, it's something quite difficult to reason about. Then detect if all necessary functions got generated, and the first class support for static polymorphism, not just as hacking around and using the static analysis, but having it natively working. So, as a conclusion, our problem was this mapping from Slang to Smalltalk, and we needed a limited amount of polymorphism. We extended the code generator, which bridges a mental model between Slang and C a bit more, because you can now write your code a bit more Smalltalky. And errors can be difficult to trace even more now. And finally, to say Slang in general is a bit brittle, but it works as a working tool. Thank you. Do you have questions?
Thank you. So, any question? I hope you can hear us.
So when you were talking about the putting the prefixes on methods, that just reminded me a lot of, you know, C++ name mangling, for instance. And so, but it looked like some of the calls you didn't actually put prefixes on. So just can you explain a bit more about what decides when you prefix or not? Because yeah, you've got one that's just store on its own.
In general, you in the direct case, so in the first case from earlier, you always prefix because you have in both cases you have some method present, like mark, so you have to prefix it. Or you could say one is more general, but I always prefix them. Here it's more of a logical view of it. It's in general the default will be generated, and then the other case will be 2. So I am store isn't, you won't see it.
Any other question?
I'm wondering if there's any big difference here between your kind of spreading polymorphism and really just a kind of aggressive function specialization, the specializing functions to the types of their arguments.
I don't really understand your question. Could you specify that?
Yeah, function specialization is a technique where by looking at the specific types of the arguments being passed, you generate another version of the function that then assumes those types.
Yes, you could say this. That's mostly done on the method base, that you say assume all markers are complete markers now, or whatever we resolve for in these cases.
Okay,
you could think this way about it.
Any other question? Then I think we can thank the speaker for his talk. Thank you. So.
No, it's wrong.
Okay, so, okay, it is now time for the keynote talk of VMLL 2023. So this year, the keynote speech will be delivered by Shigeru Chiba, who is professor at Graduate School of Information Science and Technology at the University of Tokyo in Japan. So for one of his work, JavaAssist, which was originally published at eCoop 2000, Professor Chiba recently won the ITO Test of Time Award as a recognition of the large and lasting impact that JavaAssist had on the field of programming languages. Professor Chiba, thank you for accepting our invitation, and the stage is yours.
Okay,
thank you
for... So thank you for kind introduction, and also I would like to thank for this invitation. That was a very good motivation to fly to Europe from Tokyo this time. Well, so anyway, so I would like to talk about polyglot programming through foreign function interfaces. So nowadays, polyglot programming is everywhere. So it's to me, it's like a Cambrian explosion. When I was a student a long time ago, in the previous century, the world was dominated by C and C++. Well, some small talk at that time, and Lisp. Some people love to using Lisp, but many people industrial people are using C and C++. But nowadays, we have to deal with lots of languages, and also at the university, we have to teach many languages, not only C and C++. So that's nice. And this workshop is workshop on virtual machines. So I believe many more people here loves to use a single virtual machine, which should rule them all. Yes, that's right. For example, GraalVM is a very nice seminar work. And nowadays, you can run almost any kind of languages on top of Java virtual machine, like Java, not only Java, Scala, Groovy, but also Ruby, R, JavaScript, and C and C++ on top of Suron. That's great. But I would like to give a question. So why do we need polyglot programming nowadays? And I think one of the main reasons is libraries. Nowadays, libraries are a big thing, I guess. And in particular, many programming languages, many of the nice programming libraries are non-pure libraries. For example, Python provides PyTorch, TensorFlow before, but those libraries are not written in Python. It's basically C libraries, but C libraries is wrapped around by Python code. And so we believe that's Python library. And many machine learning people and many young students want to learn Python to use PyTorch for machine learning, which is a very, very trendy topic. But they are not interested in Python code. They are interested in C code behind Python library, Python code. Same for MATLAB. Matplot. Matplotlib is a very convenient library, and many data science students are using Matplotlib on top of Python. But again, the core of that library is written in C and C++, and the Python code is just a wrapper of them. Another example is JavaScript. I think JavaScript is one of the major languages today, and DOM is very convenient and very nice libraries for graphical user building a graphical interface. But DOM is written in JavaScript, yes, but most of the DOM code, DOM library is written in C++ as a part of the browser. So it's JavaScript library, but if you want to say, I want to use a JavaScript for using a DOM, maybe this solution might not be very appropriate because the motivation to do the polyglot programming is to use kind of non-pure libraries coming with some major languages. Of course, yeah, people are working on the topic for this scenario, like by using Slon and LLVM. But today, I focus on polyglot programming on multiple VMs. So in this scenario today, I want to use standard off-the-shelf VMs and to use libraries coming with the standard ones. And for that reason, I would like to use multiple VMs by programs communicating with each other through following function interfaces. So not use one single very great VM, but I want to use, in this context, I would like to say we want to use multiple VMs, multiple standard VMs, Java VM and Python VM and Ruby VM and also JavaScript VM or Node.js. And I want to enjoy libraries, non-pure libraries on top of that. So that's the context of my today's talk. So in that context, I would like to pick up a few topics. There's two topics related to this scenario. One is the design of a polling function interface, and the other one is a collaboration among memory managers coming with those off-the-shelf VMs. The first issue is the design of a polling function interface, which is not only for the polyglot programming on top of multiple VMs, but it's also applicable to polyglot programming on a single VM. But this design issue is more serious issue in the context of polyglot programming on multiple VMs. So let's start the first issue. So this one was work presented at Gypsy several years ago. So I am a Ruby programmer today. Well, not really. It's like, because I'm from Japan, and Japan, the Ruby was invented in Japan, and many core developers of Ruby is still in Japan. So many of my friends are working for that, so I like to pretend I'm a Ruby programmer. But, all my friends working for Ruby are not good at Ruby programming because they are basically C++ programmers because they are developing a Ruby VM. And many people ask them, how to write this Ruby code for Rails. They can't answer. But anyway, I want to use Python libraries for machine learning and data science, PyTorch or Matplot. Although, of course, similar libraries are provided for Ruby, but unfortunately, they are not very powerful. So I want to use Python libraries from Ruby. And one guy implemented the FFI, foreign function interface for Ruby, which allows Ruby code to call Python code very flexible, in a very flexible way. So here is an example. So suppose you wanted to use matplotlib in Python, and the code below is a Python code I copied from some website, tutorial website. And you can, as you can see, you can write a very, very similar code in Ruby to use this Python library. So that's the power of foreign function interface today. It's nice, but there is a pitfall. So for example, suppose you want to use a deck library from Python. In Python, you write like that, DQ equal deck parenthesis bracket 235. It makes a deck containing 2, 3, and 5. In Ruby, you can call that deck function. You can use a deck library in Python by using foreign function interface, but you have to. Unfortunately, you can't write like the code like Python. In Ruby, you have to add some extra dot after deck, deck dot parenthesis. This is because this is nice due to the very flexible syntax provided by Ruby, but if you forget that, your program crashes. Or you have to, actually, the meaning of dot is to call new method on deck. So so basically you have to create some object through a deck variable, which is a reference to a Python object. But so you have to write that. Another pitfall. Both Python and Ruby provides keyword argument, but the syntax is slightly different. So in Python, again, to use matplotlib, you want to write that kind of code. You want to call plot with some LW equal 5. LW is a keyword argument. In Ruby, you can call that library through foreign function interface, but you have to be careful. You have to write, because the syntax of keyword argument in Ruby is different from the keyword argument in Python. You have to write LW colon 5, not equal. This is a very minor difference, but it's a big pitfall when you write Ruby code using foreign function interface to call Python library. And the worst thing is you can write LW equal 5 in Ruby, but in Ruby, that's a kind of assignment to LW. So it works, but the result of this code is different from what you expected, and it's going to be hard to debug. So this pitfall is not a simple thing. I have another example. Sorry. Dictionary. You can call. Suppose you want to use a TensorFlow. TensorFlow is nowadays a little bit old library. The progress of machine learning is so quick. But when I wrote this paper, TensorFlow was still kind of a popular library. In Python, first of all, you import TensorFlow. And first, you call session function to create some object, tf.session. And then you can run it with kind of extra parameters with x data argument, whose value is 2.0. In Ruby, you can do the same thing by using foreign function interface again. But first of all, you have to call new. You have to add extra keyword new instead of just simply do the same thing as in Python. And more serious pitfall is the last line. To make a dictionary, you have to use a row symbol instead of a colon. And
if you sloppy guy, and if you write x data colon 2.0 for Ruby, it works, but the result is different because in Ruby, so the meaning of this function is x data is not the label. It's just a kind of returned value from the third line, fourth line. tf.placeholder returns a value, and it is assigned to x data, and the pair of x data and 2.0 has to be passed to a run method. If you write this code in Ruby, the semantics of the dictionary construction is slightly different from Python, and the meaning of this case is it's a dictionary. In the dictionary, the key is x, the string constant x data, and this dictionary has a pair of string x data and 2.0. So it's different from the data expected by the run function. So it doesn't work. So all in all, okay, these examples are not artificial. These examples are not examples I try to find or I try to come up with by careful reading documents. I found these mistakes in some blog entries on the internet. So because one guy implemented a foreign function interface for Ruby, and that got popular, but many people try to use it for using TensorFlow and other nice Python libraries and got the problems. And it's very hard to fix bugs. So basically, Ruby use Python libraries. When Ruby users use Python libraries, basically they first Google and find some blog entries or Stack Overflow entry, and to find how to use a Python library because they are not Python guy, they are Ruby guy, and they tend to copy and paste sample code found in a tutorial and run it because they believe foreign function interface deal with everything smoothly. So that's why they wrote this kind of code, right? Because they found Python sample code, in a tutorial, and just make a copy. And they don't really care about the detailed differences of the syntax between the two languages. Well, they know, but it's. So the question is how to avoid these pitfalls. Can we do that? Can we do that? So my observation is, well, foreign function interface is very popular technique to do polyglot programming. But maybe function is not right abstraction nowadays. Well, it might be nice in the era of C libraries, C++, C++ is not really, but in old C libraries days, it should be okay. But now we want to use libraries written in a different language like Python, JavaScript, maybe Ruby for Rails. So my observation is maybe function is wrong abstraction. This is not because the Ruby's syntax is very similar to Python's, because all the examples are due to very minor differences between Ruby and Python, or similarities between Python and Ruby. But I believe this is a more serious issue. One of the reasons of the pitfall is that Ruby users expect arguments are also Python code. Because they copy and paste. So first of all, the first line is, they call tf.session, which calls session. They expected this is a Python code because they are using Python library. But it's not really Python code. It's run in Ruby, and it's interpreted in the semantics of Ruby. And all the method lookup stuff is done in Ruby, under the semantics of Ruby. So that's one of the reasons why some pitfall happens. The second one is also true. From the user's viewpoint, Ruby user's viewpoint, they wanted to run a run method in Python library with some parameters. But the arguments are computed in Ruby. Yes, we are programming language guys. The first thing we learn at the undergrad class is, okay, argument is evaluated at the caller side, not the callee side. But in case when you copy and paste the Python sample code into Ruby, they often tend to think it's part of the Ruby, it's Python code. But again, this argument expression is interpreted in the context of Ruby, so that makes a problem. So our idea solution is pretty simple. So maybe for polyglot program, in the context of polyglot programming on top of multiple VMs, we should be able to do that code migration rather than foreign function interfaces to avoid pitfalls I presented before. And because keynote talk, I would like to say, well, future VM people should consider this, and they should implement their own VMs to enable this kind of code migration to support polyglot programming. Well, the rest of the idea is pretty straightforward. So for example, this is a very simplified version of the idea. So instead of, foreign function interface gives you a nice looking code, but to avoid the pitfalls, you should be able to write that kind of code. It's like when you want to call Python library, you should say, maybe put some keyword like run Python and curly brace and write Python code. And in this case, the code within the curly braces should be interpreted in the semantics of Python, not Ruby. But because this is a foreign function interface, it's still a kind of foreign function interface. So I would like to say, this code should be still valid Ruby code. In other words, I like to use embedded DSL based on hosted by Ruby rather than pure Python code, because you can expect editors support and also IDE support if the code is written in embedded DSL hosted by Ruby in this case. So in that sense, it should not be string embedding. String embedding is one of the techniques to implement embedded DSL. The idea is simple. When you do that kind of thing, just pass a string constant to some function. And in this case, run Python takes a string constant, which is Python code, and just send it to Python and run it. So it's very straightforward. But if you use a string embedding, you can't enjoy any library support. Editor's support or IDE support. So I still say embedded DSL should be nice. And also, in typical string embedding, you would not be able to write this kind of code because LST is Ruby variable, and the code embedded in the string refers to LST, but usually it's not possible in the typical string embedding DSL, but that should be possible. So we wrote, So another example, it's a more complex example is with, because Ruby provides very flexible syntax, you can stay in embedded DSL even if you wanted to use a very complex syntax provided by Python. Ruby, as you know, Ruby doesn't provide the with statement, but because Ruby provides very flexible syntax, you can pretend with statement by using some complex Ruby syntax. And so it's possible to write it in the context of embedded DSL hosted by Ruby, but Ruby Python, run Python code takes that function and do some complex thing and send it, and interpreted it in the similar semantics of Python and send it to Python and get the result. We wrote some simple library called Yadorigi, which allows you to write this kind of embedded DSL. So the idea is very simple. It's this library provides just one function, a refi, which takes a function, lambda function in Ruby, and generate abstract syntax tree of the function. So that's it. The mechanism of this function is only that. But if the future BM, every future BM provides this mechanism, you can implement some nice embedded DSL on top of the host language and minimize kind of pitfalls caused by the differences between two languages. Well, so just for someone who knows Lisp macros, they might say this is the same as a Lisp macros. Yes, but the Lisp macro is basically takes an abstract syntax tree and returns abstract syntax tree. But this refi mechanism takes a function. It's a kind of first-class function and returns the abstract syntax tree. So you can write some convenient function to provide a better programming interface and so on. So it's a minor issues. Anyway, move on. So that's one thing. And the second thing is collaboration between memory managers of the multiple VMs for polyglot programming. So this was the work presented by us at this year's PLEI. So it's a little bit new. Again, I'm a Ruby programmer today. And I want to use a DOM library in JavaScript for building nice graphical user interface on web browsers. Well, Ruby provides the old TickleTK library. That's a kind of very old-fashioned library for my generation. It was very popular in the previous century, but now we are in 21st century. So TickleTK library is not nice. Today, the best user interface is web browsers. So we want to use DOM library to implement some graphical user interface for Ruby. So in this case, I myself implemented the foreign function interface between Ruby and JavaScript. I believe that's a nice library, and it's open source. So you can, by using this library, you can write a Ruby code which runs in an independent process and calls and invokes a standard browser like a Safari or a Chrome or a Firefox as a separate process. And the Ruby program communicated to the browser through a kind of socket, TCP/IP or socket, and draw any kind of web page by through the FFI. So look at that code. It's more like, it's a Ruby code, but it's more like JavaScript, if you know the JavaScript. You see a title and button are Ruby variables, but it refers to JavaScript DOM object. And you can call any method on those variables and manipulate web pages. So it's nice. It was nice, and you can write this kind of sample code. You can put some button on the browser browser page and let users click that button and do something nice. But as you know, event handlers is a very easy way to make a cyclic references, and which causes a cyclic garbage And typical FFI implementation makes a memory leak. You see, so here left-hand side is a Ruby code and right-hand side is JavaScript. And because that code is written in Ruby, but if you run this code, in Ruby, you make a callback object, and that refers to button DOM object, which is in JavaScript. And of course, the button object in JavaScript refers to Ruby objects because it's callback function. So it makes a cycle. And the typical FFI interface uses a kind of reference counting garbage collection. So it's easy to make a memory leak because basically reference counting GC cannot reclaim cyclic garbage unless you use some tricky things. Yeah. And the reason we have to use a reference counting garbage collection for FFI is because these two programs are separate in separate processes, and there is no way to look at the memory heap in the opposite side. So that's a problem. The people who pointed out this problem was not me. This problem was presented by different people at UPSA 18s 5 years ago. They are Google people, and they are developing V8 VM and also Blink HTML renderer. And because, from our viewpoint, DOM library is in JavaScript, but from the implementer's viewpoint, JavaScript is run on V8 VM, and HTML renderer is running in a separate component, which is Blink in the case of Google Chrome. So their solution was, they proposed a cross-component tracing. So their solution was to modify V8 and Blink for remote tracing. As I said, reference counting is not good at reclaiming cyclic garbage. So they modified the V8 and Blink memory managers and let garbage collectors trace references between V8 and Blink because both of them are in the same process. So it's technically possible, although from the software engineering viewpoint, it's not an easy thing because the two components are developed by separate teams, although they are both working for Google, but Google is a big company, so they communicate each other and try to minimize the modification of the components to enable this. Nice, yes, presented at UPSA, great. But unfortunately, we are not employee of Google employee. A bunch of my previous students are working for Google, but I don't have any ways to ask them to modify V8 for us. So we have to find a solution which doesn't modify V8. Good news was I have a very good connection to Ruby people. So it's possible to change Ruby VM, although Ruby's garbage collector is also a production VM, production garbage collector. So it's very difficult to modify it. But changing a VM bit is okay. I just write an email to my friend. I have this problem, and do you have any good ideas to customize a VM, Ruby VM? And he told me there is a function, right? It was not exposed, but it's easy to use. So our idea is to implement some coordinators between V8 and Ruby's garbage collectors without changing garbage collectors. And so because we can't modify the V8 garbage collectors, so we cannot implement some remote tracing. But idea is pretty simple. So we make a kind of local reference graph in Ruby and copy that graph into V8 world and ask V8 garbage collector, okay, to trace them and reclaim garbage. And of course, this is very may come with a big overhead, but we assume the remote references are not many, because in a scenario, we just want to use the DOM libraries in JavaScript. Most of the code is running in Ruby VM. Just want to use, DOMs. So the number of remote references are not many. So it's not a really, complex polyglot programming. So that's why this idea works. Let me simply show the brief overview. So here, look at that B object, which has some icon of pin. It represents the reference counters. So because the reference count, the number of reference count is more than 0, so it is pinned down to avoid accidental reclamation. So basically, garbage collector, both Ruby garbage collectors and JavaScript garbage collectors look at only local references. So that's orange, just arrows. And to avoid the reclamation of B, object B, we use reference counters. But what we really want to do is global tracing. We want to ignore reference counters, and just we wanted to look at arrows and, over across the Ruby and JavaScript. And the idea is just copy the kind of part of the object reference graph in at the Ruby side to JavaScript, and ask the Ruby JavaScript garbage collector GC to trace all the object graphs and reclaim garbage. So that's an idea. So, and let me show a little bit more complex case. So look, this is an example. We have a bunch of objects, and in this example, garbage object F, G, H, I, and J are cyclic. It makes a cycle, and it's a garbage. So the goal is to reclaim them. So first of all, we make a reference graph. So blue one and green ones are reference graphs. So basically, reference graph is a local reference graph in Ruby. And to make this graph, we had to modify a Ruby VM. But the modification was very, very small. We didn't modify the garbage collector. And the tricky thing is, so we first run a normal tracing. So it makes first we trace is a blue. I mean, we count up, we enumerate all objects reachable from the Ruby root, okay? And in this case, object C has to be live because it's reachable from Ruby. And after that, we look all the incoming reference from JavaScript to Ruby, in this case, in a reference to object I, and trace all the traces all the references from I, and to see which outgoing reference from Ruby to JavaScript exists. So in this case, object G is reachable from H. Look at the reference from F and G, from F to B. This is not traced because anyway, object B is reachable from the root, so we can ignore them because the goal of this idea is to reclaim cyclic garbage, so we can ignore all the blue objects. So this is why the performance overhead is not large. Because most of the live objects in Ruby side are reachable from the Ruby root. So we have to run kind of tracing from the root, but the tracing green thing is not a big issue, big thing. So after that, we copy kind of blue edge and a green edge to the JavaScript side. It's compressed. It's not the whole, we don't really copy all the Ruby objects into JavaScript side. We just simply make a copy as a kind of graph, from and to. So this double edges are a row. And run a garbage collector in JavaScript, and suppose the JavaScript garbage collector reclaims object G and H, because they make a cycle, but it's not reachable from the JavaScript root. That's it. And then after that, because the JavaScript objects are reclaimed, Ruby objects I and J and F are also automatically reclaimed by using some normal reference counting. And after that, we restore all the reference counters, in this case, C, and run again, run the mutator again. So that's it. Well, at the beginning, we worry about the performance overhead, but as I said, most of the live objects are reachable from the Ruby root. So the actual performance overhead was not large. So it works. But when I tested the many benchmarks and examples, we found that in a real system, this should not work. This didn't work. Because this algorithm assumes that we can run a garbage collector in JavaScript. We can run a full garbage collection in JavaScript just after copying object graph, reference graph. And after the garbage collection finishes, we restore all the reference counting and run the code again. But as you know, a modern garbage collector is very complicated very complicated program, and it's not realistic to assume that. And we are not really sure, but according to our observation, to implement this reference counters, we use a lot of weak references. And JavaScript garbage collector seems to recognize weak references accessed just before the garbage collector starts as strong references. So to make all the things, you have to touch all the remote weak references, and that makes all these references strong references, and then JavaScript garbage collector ignore those weak references. So that's why the system didn't work. So we had to come up with improvement. So we stopped running garbage collector just after copying reference graph. We just copy a reference graph to JavaScript, and before JavaScript garbage collection starts and finishes, we resume mutators in Ruby, mutator threads in Ruby and also JavaScript. And of course, this is problematic in case because a mutator thread may change a reference graph in Ruby just after copying a reference graph and before restoring all the things. So we have to maintain the copy of graph in JavaScript be consistent with Ruby side. So here's an example. Now we have a graph from C, D, E, F, and G. And so because according to the algorithm I presented, so we make a reference graph and copy the graph into JavaScript. Looks okay, but now we resume all the Ruby threads before finishing this garbage collection. So after resuming a JavaScript thread may call a method on B with an argument, which is a reference from C to D. So basically, JavaScript program may pass a remote reference from JavaScript to Ruby object as an argument. So which is very problematic. Because the receiver method, the called method B on B, receives a remote reference from JavaScript to Ruby. So they may use it, and they may make a new reference from B to D in Ruby side. And now, kind of reference graph in Ruby is changed. We look at the green one. So now we have a reference from we have a path from A, B, D, E, F, and G. So according to our algorithm, we have to make a kind of copy of reference graph in the JavaScript side to make it consistent. So in that case, a reference has to be, we have to have a reference from A to G. But because this change was done after copying a graph, so it's not reflected on JavaScript side. So after that, JavaScript program may delete a reference from root to C. In this figure, it's named Q. So then, JavaScript garbage collector may reclaim C and G because they are not reachable from the JavaScript root now. But from the viewpoint of a global reference, object G is still alive because we have a path from A, B, D, E, F, and G. So that's problem. So our solution is to install some sort of a barrier. We named it a kind of send barrier because in this case, we have to detect when a JavaScript program sends a remote reference from Ruby to Java, to Ruby. JavaScript to Ruby. So our barrier monitors all the arguments and see whether that argument is a remote reference or not. And if it's a remote reference, they stop the kind of copying and restore all the reference graphs, reference counters, and so on. And it cancels the garbage reference counting garbage collection. So if we properly install this send barrier, when JavaScript program passed the remote reference from C to D to B, copied reference graph is eliminated, and all the reference counters are restored, and everything works well. Although we lose the chance to reclaim C later. We lose the chance to reclaim some cyclic garbage, but later we assume that reference counting garbage collection is run again, and finally they are removed. Well, it's time to stop. So, I quickly introduces our work on polyglot programming in the context of the use of multiple VMs. Again, to summarize, I would like to say one of the big reasons to do the polyglot programming is to use their non-pure libraries. I mean, libraries written in C and tightly integrated within a virtual machine. So to do that, we have to consider the design of foreign function interface. As I said, function might not be the best abstraction in this case. Maybe code migration is a better abstraction. So the future VM should support that kind of foreign function calls or code migration, as I said. And the second topic was memory management. Well, if you run all the programs written in different languages on top of the single VM, we don't have to care about memory management because memory management is done by that single VM. But in my context, we have to run multiple VMs. Some are separate processes, some are in the same process, but still from the software engineering viewpoint, integration of the two memory managers is not simple work. So in that case, our proposal is to introduce some collaboration framework between memory management. We had to modify the Ruby VM because basically Ruby VM doesn't provide a mechanism to implement our algorithm. But again, future VM should provide some interfaces to support remote cross-component tracing proposed by Google people, or reference graph garbage collection. So that's my talk. Thank you.
Thank you. That was a very enjoyable talk. Near the start, you suggested that one VM to rule them all wasn't a brilliant idea.
Well, I never say it's not the
No,
brilliant idea.
Sorry. Okay. But that one VM you were thinking about was the JVM. Do you think WebAssembly might be a better single VM to rule them all? That's one question. And the second question, if I may, very quickly, how do you get around the n squared problem where
Excuse me?
you? Oh, sorry. The notion that for every pair of virtual machines, you'll need to engineer a distinct foreign function and kind of bridge between them. Thanks.
I lost your point. So, do you?
If you have 5 other languages, you need 5 interfaces. Each one needs interfaces for 5.
Yeah, that's a good question. So far we are focusing on the 2 VMs. With 2 VM scenarios, and for example, for memory management, we have to consider multi-party cases like 3 VMs, and also, yes, as you said, the WebAssembly is getting popular, and if you use in a case WebAssemblies, you have you can easily make 3 or 4 components, and every component has their own memory manager. And in that case, you have to deal with many, very complex situations. And well, actually, we are working on that, but we don't have any nice solutions so far. And I also got a message, contacts from other people who are also interested in such complex situations. So that might be a nice, interesting research topic in future. Yes.
Hi. So I think you were able to modify the Ruby VM for providing what you want, but didn't you need to modify like VA as well? Like, what was the thing that was there in the VA and was missing in the Ruby side? Like, were you able to check if the reference from the JavaScript is from the root or not without modifying the VA?
Well, our assumption was we don't want to modify the V8 at all. We want to use just off-the-shelf V8 engine. But the mechanism we need is to trace objects in that local environment. So if the V8, in the future V8 provides such a mechanism to implement some sort of tracing, then you can do the same thing. But in that case, the host is a JavaScript, a V8. And Ruby, we don't have to modify the Ruby VM at all. But our algorithm needs at least one language has to provide kind of tracing mechanism, and trace all the objects reachable from the root. And that's not available now, at least on V8 as far as I know.
Maybe I still don't follow. So why just only one of these requires the implementation of that? Because so you can communicate the root path from Ruby to JavaScript because you can modify Ruby, but let's say there's cyclic reference from both languages. How do you communicate the path from, say, from Ruby to JavaScript and then JavaScript to Ruby? You can go through from Ruby to JavaScript because you can modify the Ruby VM, but then if that goes back to Ruby, how do you know from the JavaScript reference that the Ruby object is?
Okay. So basically, remote references are implemented in a special way anyway. In this case, we actually, to simplify this explanation, I didn't mention that, but usually the object C is kind of proxy object. So its implementation is not the normal JavaScript object. So object C knows this reference is not a normal reference. It's not a local reference. It's a sort of it's a typical implementation in this kind of thing. So it knows that all the program, even the user level libraries can recognize remote references. But question is how to get the root objects some root objects are in the stack frames. And usually there is no way to list up all the objects are reachable from the root. And that's pretty, from the implementation viewpoint of ZC, it's very complicated in case of concurrent programming.
Okay, thank you.
Hi, great talk. Maybe I misunderstood something or I didn't understand something. So in your view, what's the motivation in the case of the foreign function APIs to go from high-level language to high-level language to low-level language? For example, you mentioned the PyTorch case, right?
Mm-hmm.
PyTorch is a Python, let's say, face, if you like, to go to CUDA, DNN, or these low-level APIs for GPU programming. But in this case, you are going from Ruby to the Python to C or C++, right? So do you see that that's a better view, and what's the benefit of doing that?
Well, most of people are not care about the details of the implementation. They don't know how PyTorch is implemented in Python. They believe all the code is written in Python. And yes, you are good engineers, so you can just retract C libraries from PyTorch or TensorFlow and port it into Ruby. It should be easy to write some wrapper code.
Yeah,
but most of people want to use PyTorch as it is. They simply just search Stack Overflow and get this kind of piece of code to use some
Okay,
nice
I buy that. So you're mentioning because of the ecosystem, it's easier to find documentation in the high-level part than the low-level part.
That's right,
Okay,
that's
I
right.
buy that, yeah.
And
Because
I think that's very important nowadays.
I do agree, yeah. Okay, thanks.
Thank you for your talk. Do you have any thoughts on the large-scale software engineering costs of systems that you build from different, possibly many languages? So in my experience, it's always very hard to, especially if you go slightly more exotic, maybe not Ruby, but R, and you combine that with something like JavaScript, TypeScript, it's really hard to kind of find people that actually can work on the combined system and just instead of just one part of it.
Yeah, but if you look at the history of the programming, many people are struggle with always polyglot programming. For example, nowadays, if you wanted to develop web services, you have to write a code in what is Apple language? I forgot the name. Yeah, and also Java for Android. No, it's not Java. It's and also SQL. Still, even nowadays, you have to write a SQL code for accessing a database. And sometimes, if you're working for the financial industry, you might have to write a COBOL code to use legacy, system and so on and so on. So anyway, I know it's not a very good solution. As I said, as I said at the beginning, the best solution is to use a single VM. Single VM should rule them all. But in practice, we still have to deal with lots of we have to deal with the multiple languages and write appropriate code, because not all the software is written in open source, and every people has their favorite language. Some of my students love the Haskell, and he wanted to write anything in Haskell, and some others still like Python and so on. So that's my observation.
Okay, thank you.
Thanks. This is a question about the language syntax similarities between Ruby and Python. Mm-hmm. You showed near the beginning of your talk some blog articles where Ruby programmers were using the PyCall FFI, and they were using native Ruby syntax, and it was giving them the wrong answer because somehow that didn't map well onto the Python abstractions. So I think some of those examples you showed with your blog articles of 2018, 2019, and so on, ChatGPT or large language models these days, do they make the same mistakes when you ask them to synthesize PyCall code in Ruby, or is it clever enough to do it properly? Have you investigated that?
That's a difficult question. I don't have any clear answer to that. But I still believe syntax is one of the fun part of the design of programming language. And also, it's a kind of, I often think my research area is not science. It's more like humanity, social science. Because, we programming language people propose many nice ideas. And, we've been proposing the best way to develop complex software so far, not only me, everyone. But some people, not some, many people are still, it's like it's a humanity, right? Old people still want to stick around C and C++. For example, people working for embedded systems love C++, and not C++, C. They still love C. And web people loves, well, it depends on the generation. According to my observation, it's not a good, politically good thing to talk about the kind of generation, but well, my favorite phrase is that people tend to stay around the technologies which was the best in age 20s, or I say, when they first learned computer programming. So if the Python, for some people, Python is still best language because they first learned Python and they get excited. So they want to stay there. But unfortunately, technology is changing. And I believe that Python and Ruby are still good languages, and I love the dynamic programmings. But if I talk to my young students, they love the static programming, right? Static typing, right? It's funny because Ruby and Python were sort of a language against old-fashioned statically typed world. At that time they got bored with static typing. At that time, type system was not very strong. Then so they are excited with Ruby and Python. It's very productive. But then they recognize that static typing is better for developing a large software. And now the young people saying that, well, TypeScript is great. They don't like JavaScript. But I say there are still pros and cons and benefits and drawbacks. So we have to deal with. So in that sense, we still have to deal with multiple languages. We have to select a best language for the applications. So that's my, sorry, it's not the exciting thing, but it's.
Any more questions? Okay, then let's thank one more time.
Thank you very much.
So this is the end.
talk rather than write.
We're 10 hours now. That was 8 hours from Boca.
Hello?
Hello.
Are we good to go?
Yeah, all good on my end.
Okay. All right. Well, welcome to this the third. I think it's the third session of VMIL, and we have 4 talks in this session. The first of which is, as you can see on screen, is going to be given by Mitesh Mehta. The title of the talk is Debugging Dynamic Language Features in a Multi-Tier Virtual Machine. And I'll hand over to you, Mitesh.
Thank you so much. Hi, this talk is about debugging dynamic language features in a multi-tier virtual machine. So this is our team. We are from IIT Bombay and IIT Mandi. So unfortunately, couldn't be there for the offline presentation, but here we are. So let's start off with dynamic languages in general. So dynamic languages are great. In the focus of this talk is on the R programming language, but the concepts apply to other languages as well. So people write a lot of dynamic language code, and particularly the features that I find to be the most interesting are dynamic typing. It helps us write neat and tidy code. First-class functions and environments help create a nice abstraction around a lot of code that we write. And then we have some subtle features that are made by language designers, like lazy evaluation. And this is one feature which a lot of languages implement in their own way, and the places where it tries to behave lazily or not is defined by each language. And after that, we have some less common features like runtime reification of environments and access to the runtime stack. And this is a feature that I don't think many languages would support for obvious reasons, but it does come handy in R. And after all this, we have the most favorite language feature for all compiler engineers, that is eval. And yes, it makes compiling and optimizing challenging, but it does come useful in debugging. So these are dynamic languages, and running them fast has been a big challenge for a long time. And one of the common ways of speeding up these languages has been to design VMs and optimizing code on the fly. And in context of R, a paper by Olivier et al. In DLS 19 presented an IR that tried to optimize R code. And one footnote from that paper really resonates when you start working with R. So the footnote says the sound one makes upon realizing that arguments can modify the environment of the function they are given to, and such dynamic language features, even though they make writing code much easier for the end user, makes it really challenging to optimize for. So a 10K feet view for a VM to an end user is it's a black box to which a user passes a program, and somehow it speeds it up. So you have a 10x speed up, and sometimes when things don't go as well, you see a 300 times or 1000 times slowdown. And this is a problem that many VMs face, and this is something that plagues a lot of VMs in the current day. And the way these VM works are very interesting. So they do a bunch of things behind the scenes and usually not visible even to the people who are experienced in that language, and only known to the VM implementers is things like compilation, profiling, calling conventions, specializations for different contexts, and so on. And really, these are a lot of complicated integrations that do indeed bring in a lot of bugs, and which make it really difficult to debug. And not just for the maintainers of the virtual machine, but it's also difficult to find and reproduce bugs, because there'll be things like the garbage collector that sometimes eats up your memory, and this is a real problem. And so in this talk, we want to focus on three aspects of the virtual machine of our interest. And the three aspects are interpretation, profiling, and specialization. So what exactly happens when you interpret code? Because an end user writes code line by line, expecting that each statement does what it's supposed to and it gets stored somewhere in memory, but that's not really what happens behind the scenes. And profiling, what exactly does the VM profile, and is there something that the user can do to write better code? And specialization is something that many VMs do to generate code on the fly for specialized use cases. And these are the aspects that this work focuses on. So we work on the Russia virtual machine, which is an interpreter for the rear bytecode. So our tool is called DREAR. So D stands for demystifying and debugging, where rear is the rear bytecode that the system interprets. So looking at the VM view from end user perspective, like the kinds of questions that one might have is, okay, I've written, so let's consider hello. Hello. Uh, am I still connected? Okay, so I'll continue. Uh, okay, so starting back, maybe there was a brief disconnection. Yeah, so from a slightly more experienced user, we might, who writes a lot of R code, you might, he might experience the system sometimes running fast and sometimes running slower. But what might happen is the runtime might optimize for a different specialization, and hence the code runs faster. So, and one of the last feature that language designers are interested in, what happens when we try to increase the expressive power of the system. Let's take this piece of code, for example. Let's say we have a function foo that iterates over I from 1 to 20, and when I reaches 5, it executes f of break. So what does this even break mean? How does it get interpreted? So in case of R, which supports lazy evaluation, this is indeed not evaluated and just simply gets passed to f. And when f is executing, it instead passes this argument back to g. And when we do that and assign it to a local variable inside g, it gets forced, and when this force happens and when the break is executed, it jumps and the control flows outside the for loop. So typically not anyone would write such code, but this is a valid piece of our code. And when people optimize when people try to optimize these functions, these weird things have to be accounted for. So the Russia JIT compiler takes into account all of these corner cases when optimizing code, and contextually specializes different functions. And because of this, it does experience a huge warm up and does have strange compilation behavior sometimes. And in order to study these, there are different tools that we developed over time. And one of the first ideas that we had was to just visualize traces. So the question was, do contextually specialized functions even ever get used, or is it the case that over time only general functions remain and the specialized versions get discarded? So in this image, you can see all the colors, and all of these unique colors represent different contextual compilations for functions. And as time progresses, we see that a lot of these different colors emerge, and they are not dominated by a single color, which means a lot of these compilations are indeed useful in the system. Apart from studying traces, one might also consider looking at call graphs to understand how the specialization behavior works. So in this image, there are two root nodes, that's the execute on the left and one execute on the right. The execute on the left is the interpreted version of execute, which does a lot of, which further calls a lot of different functions, and these are non-optimized versions of execute. Whereas on right, we see optimized versions of functions that are optimized version of execute, which reduces the call graph significantly because it just managed to inline most of these functions that get further called. And an other popular approach to debugging is event query, where you store a bunch of events, and for a problematic event, you might try to work backwards. And this was also one of the tools that we developed to help us debug certain aspects. So the point I'm trying to make here is it's just about selecting the right tool for job. There is no one size fits all solution, and uh, the tool has to be specialized for a special use case and has to show the least amount of information that is useful and it's easy to use. So this is our tool. It's called drear. So it can load up the function on the left. So this shows the rear bytecode. The second block that's below it shows the current closure, the way it was interpreted inside the system. The third block shows the environment. Fourth one shows the stack. The fifth one is the call graph, and the sixth one is the lattice of context. So I'll switch to a small demo of how our tool works. So let's consider function f, which calls g, and g, which calls foo, and see how the runtime behaves. So the way we connect to a visualizer is using an API call in which you pass the server address as the argument, and then it simply connects to the viz. So when the program is started, the runtime pauses at a relevant event and shows all the debugging data and the data that was shared from the backend to the front end viz. and the viz, as you can see, it's on the 0th bytecode, which is to be executed, and the environment already contains A and B, which were passed to it. And also the stack contains the promises that were passed. So as the execution progresses, and we can see how the stack updates and the function is pushed on the stack, followed by the promise being pushed on the stack. And when we step into the call, we see the call graph update and more things emerge on the stack as we continue with our computation. So at this point, when we are executing bytecode offset 7, you see it says load var cached A, that is simply the argument A. And if we look at the environment, that it's an promise which is not yet evaluated. So now when we try to step through, we will end up inside the promise and we would evaluate it at this point. So as we continue evaluating, we see that different feedback slots also get populated. And so let's just restart the execution from this point on to show you how we can modify the runtime state to see different aspects of the system. So we quickly step through to the offset that we last reached, and instead of directly executing offset 7, we will first update the environment to change it from a promise, and the binding now points to a simple integer. And now when we step through the bytecode, we would see that there is no promise to be evaluated and the step function simply just steps through. And if we look at the feedback, we would see that state before last force flag is set to a value, which means it was never a promise, and the code sees as that it was just a value that was passed. So evaluating such behavior is useful in context of R because promises are expensive. They require more code to be generated and maintained. And passing eager values is in general fast as a calling convention in R. So when the program exits, it simply disconnects. So let's now try to connect one more simple example. And so this is context.r where a function foo is called or connected to the viz, and we now call it with two different kinds of contextual arguments. So the first kind of call was with two integers, and we see that the feedback slots end up storing that it's an integer, and the s denotes that it was a scalar value. And one interesting thing to notice here is the value of A and B were passed as evaluated promises, which are just values that won't have side effects in R. If we continue our execution through the second call to foo, and if we continue to the third call, we will see that a new specialized version of foo was created and the lattice of context updates. So we are at line 13, and we can see that this call ends up compiling foo for a specialized version and will dispatch to native code. So continuing with the execution, we see that the feedback slots at 9 and 23 also get updated to denote that promises were passed. So this means that vectors get passed as promises, whereas integers get passed as evaluated promises or just values in case of R. And as the execution proceeds for the second contextual call, we see one more specialized context emerges. And in this case, we see even though we had a specialized context passed, the runtime decided to compile a more generalized version, which will suit more contexts. So the runtime behavior changes from run to run because it has a lot of heuristics that decide when compilations will happen, and this is just an example of that. So continuing with my talk, so what we were able to use this tool for, so this tool was meant to be a learning tool and to discover small, simple bugs that might exist in the system. And what we found was there is an implicit return that every function generates. And when you use the keyword return, redundant return also gets generated. So this is just a small redundancy in the generated bytecode that increases bytecode size. Something more subtle is that we see the bytecode state as it progresses over time. We can see that the context, the feedback that's collected gets generalized. So the first call here was recorded as an integer scalar, which was passed as an evaluated promise. Whereas in the second state, we see that the S is gone, which denotes that it can be a vector of integers instead of the smaller context that is a single scalar integer. The third image shows that a specialized version was created to handle simple integers. So these represent the predicates under which the compiled version is valid. For example, the first predicate says that there are no explicitly missing arguments. The second predicate says that the correct ordering was passed. The third predicate says that there were not too many arguments. Believe it or not, in R you can pass more arguments than expected by the function, and those get interpreted in special ways to support specialized dispatch. And then argument match, which means the arguments match the order in which they're expected. And the other predicates are simple, that say that the 0th argument is eager, it's non-reflective, it's not going to be an object. It's a simple integer, and the number of missing arguments is 0. And the final state is when we pass a different kind of an argument, we see it gets even more generalized to say that the feedback here says that it can be an integer or a logical and maybe a promise. So feedback slots are fixed size slots that appear as inline caches within rear, and they store a lot of field values that were recorded at that point. And the DREAR tool can be used to modify these values and see what happens in the runtime. The conclusion of this talk is that specialized tools are really useful in gaining insights, and mature frameworks like React making these tools really easy. The bad is there is no one size fits all solutions, and if you keep creating these tools for specialized problems, the documentation is really hard. So a lot of these tools that we made earlier are not maintained, and it would be good if there was a generalized framework where all of these could be fit into. So the road ahead is try to see how much of this work can be retrofit for other use cases. And an outcome of this tool or our work is being presented at UPSLA a few days from now, which is on reusing just-in-time compiled code. So this is in context of R and will be presented by Jan. Thank you.
Any questions? Okay, we don't have any questions here at the moment, but that was a very interesting talk, and thank you for that. We shall move on then to the next talk. Thank you. Session is entitled Array Bytecode Supported Microjet, and this is work from University of New Brunswick and IBM by the looks of things, and Ken Kent will present.
Correct. All right, hi everybody. My name is Ken, Kenneth Kent, but everybody just calls me Ken. I'm here to give a talk, Array bytecode support in microjit, which was conducted with our team. Shubham Verma, who's a master's student looking at finishing very shortly. In fact, I should be reading his thesis before I get home. Harpreet Kaur, who's the PhD student who's working on the larger part of the project, and Marius Purview, our partner at IBM. So I'll try my best to do Shubham proud. So the obligatory second slide of the outline of the talk, I'll give you some background on the problem, some of the technologies that we're working around. Since it's with IBM, then we're using TRJIT and OpenJ9, which some of you might be familiar with. We'll talk about microjit and how it fits in, some of the motivation for the work in supporting the arrays, design and implementation, followed by some evaluation and discussion, and then the future work and conclusions. So on the background side, as we all know, just-in-time compilations in JVMs allow us to enhance the performance by compiling it on the fly, and it merges the benefits of effectively having the interpretation and the dynamics and the compilation just when we need it. What we do know about JITs, however, is that one JIT doesn't actually solve all problems. Depending upon your application and the instance, different JIT techniques and approaches work best. So with multiple JITs, the aim is to minimize the overhead and enhance the JVM efficiency. And what we're looking at here is recognizing that one JIT doesn't solve all. OpenJ9 uses uses the Testarossa JIT, and it's a great JIT, but it does have its fallacies, as we'll see. So the Eclipse OpenJ9, it's IBM's contribution. It was originally J9, and it was delivered by IBM, and then it was flipped over into Eclipse Foundation, and it was split into two pieces, OMR, which is the underlying base, and then OpenJ9, which sits on top of it and sucks it in. Overall, OpenJ9 was designed for quick startup, low overhead, and high throughput. That was what it was designed for at the start. Arguably, it's digressed or changed in various ways since then. The compilation process checks for precompiled methods, and it uses the interpreter or JIT based on the invocation, and it tries to balance speed and resource optimization. The JIT that's actually used within OpenJ9 is the Testarossa JIT, and that's the default, and it uses selective compilation amongst other optimizations to try and bleed out as much performance as it can. So one of the things it does is it goes from cold to scorching. So as the application's running, it's collecting profile information, and as it hits various thresholds, it then does yet another compilation to try and bleed out some more performance. In addition to that, it employs the shared class cache to try and tuck away any information from previous runs and use that information to kind of get ahead of itself in terms of ideas about profiling. And then it also uses some ahead-of-time compilation. So when we're talking about arrays within OpenJ9, we need to be aware about how they're actually implemented. And within OpenJ9 itself, it uses multiple GC policies. Two of note in particular are balanced and metronome. These are region-based garbage collection policies, which effectively means it divides up the heap into regions, and these regions can be scattered throughout or reordered, things of that nature. When you're storing arrays, effectively large arrays means that it's going to be stored across multiple regions, and this causes problems because the regions may not necessarily be one after another or contiguous. So the way in which this is dealt with within OpenJ9 is the idea of using a spine, which effectively is a tree-based structure, keeps the head of the array, and then pointers off of that to regions. Each region contains an arrayoid, and an arrayoid is simply a chunk of the array itself. So you can actually split up the array across multiple heap regions. And at the end of it, we have a chain of leaves, which effectively holds the remaining pieces that don't fill an arrayoid or can be jammed in with the object itself. In order to try and improve the performance with some of the JNI calls and things of that nature where it's expecting contiguous arrays to be accessible. It employs a double map, which effectively utilizes some of the operating system's virtual memory space to actually remap those regions back into a contiguous manner. Okay. So arrays are not contiguous, short order of it. So TRJIT and MicroJIT and OpenJ9. MicroJIT we previously presented at another conference. It's a lightweight, non-optimized code compiler for fast startup, and the way in which it works is essentially just template-based compilation. So for each of the bytecodes, it maintains a template. If it recognizes that a method can be, all of the bytecodes within it can be templated, then it will do so, compile the method, and then it invokes the compiled method instead of the interpreted one. The nice thing about this is that it's very fast in terms of compilation. There's no optimization, just a straight templating. And it can be used alongside of TRJIT. So with it enabled, it gives us quick compilation and it's much less optimized than TRJIT. TRJIT's delayed and it gives us a more optimized compilation later on. And so effectively, if we use them together, the idea would be that MicroJIT would have a lower threshold. It would kick in earlier. It would perform the compilation. We'd run with the templated compilation method for a while. Once we hit a higher threshold, then we would flip over to TRJIT and then start recognizing that the method deserves more optimized compilation. Did I go forward? I did, yep. So the MicroJIT performance in general, it's faster than the interpreter. When we benchmark it against the interpreter directly, it is faster. Its efficiency is enhanced by supporting more bytecodes. Effectively, if a method does not have all of the bytecodes within it supported by the templated JIT, then effectively it won't compile the method and it'll mark it as uncompilable by the MicroJIT, and it'll defer it to compilation when it hits the threshold for TRJIT or continue interpreting. What this effectively means is that we need more bytecode support in order to get more MicroJIT compilation. And the reason for this is because the interpreter to MicroJIT switches can be quite costly. So effectively, the more we can MicroJIT, the better the performance we can achieve. So here's a diagram to try and show the control flow. I criticized Shubham about this last night. So the diamond at the top, method already compiled, should mean this method's already TRJIT compiled. Okay, so effectively when a method is invoked, we first see if it's been compiled. It's not hitting a threshold. If we have the compilation of it, we just directly go and execute the compiled code and we're finished with it. If we notice that it hasn't been compiled yet, we decrement the method invocation count. Just a straight counter is all we use for MicroJIT. Once we get to the point that we've hit the count for the MicroJIT, then we'll compile it with the MicroJIT. We'll store that compiled method, and then we'll invoke that. Once we exceed that threshold, but now we start to hit the TRJIT threshold, then we default over to the TRJIT compiler. It'll then compile based upon its first level of profiling, and it'll advance from there with normal TRJIT compilation. In the event we never hit any of the thresholds, because it's a rarely invoked method, then we always divert back to interpretation. So the motivation for our work is that currently there's no support for array bytecodes, such as new array, array length, the star A load and the star A store bytecodes. Methods with those array bytecodes effectively switch back to the interpreter. So as soon as we look at them for MicroJIT compilation, we see one of those were there previously. We just effectively mark the method as non-microJITable and then defer it to interpreter until we hit the TRJIT threshold. So by effectively having these bytecodes, now we can, any methods that contain them that was blocking us before, we can now MicroJIT and get that performance improvement. The compilation phase includes the generation of metadata. It does the pre-prologues, the prologues, and the body generation. So the meta generation phase involves parsing the method signature, mapping the incoming parameters, and allocating the code cache for the method. The pre-prologue generation phase includes instructions to detect if the program stack is getting too full. And then the prologue generation phase includes instructions to save the previous base pointer and certain registers onto the stack. Then it sets the new base and stack pointers for the method. And the body generation is effectively taking the predefined template. That predefined template's written in NASM. And then with that, we copy and patch it from the code generator with the buffered addresses into the code. So here's an example of the IA store bytecode template. You can see here where we grab the values from the operand stack, stick them into the registers R11 and R12. Right? We grab the reference, put it in RAX, then we perform the evaluation, right? And we store the value at the index of the array. The template of the new array bytecode was a little bit more complex, simply because of the fact that new array means that we have to do memory allocation, and memory allocation means, well, what's the size of the array? If it's a small array, then we can take the fast path for the contiguous arrays, which effectively allocates the memory in the thread local heap, and it's no problem. If, however, the array is large, then we had to actually deal with that through a helper function. So we had the JIT new array helper function, which we patched in from outside of the template. We invoke it. It does the allocation for us where it has to create the spline, or the spine, the arrayoids, and any leaves that are necessary. Registers are set up and calculations for each of the primitive data types occur at this point. For evaluation, we'd used a basic desktop machine. Okay, here's the specs here from the paper for those of you that are interested. And we measured our time using the log files. The testing and the benchmarking that we used, we developed our own regression testing suite for the microJIT. This was effectively based around the idea of testing that each of the bytecodes that we implemented operate correctly and test the corner cases. We don't really use it for performance measurement, just for verification that it actually works and is doing as it should according to the spec. We did use the DeCapo suite for benchmarking and performance, and most of the benchmarks there are running, and we use that to actually try and judge the performance of the system overall. So we evaluated the JVM memory, the compiler performance, and so on. So to give you a little bit of a snapshot of the results, here's a figure where we show the performance of our microJIT against itself with arrays and without arrays. So without arrays is the blue line. Effectively, if you run microJIT, that's your base case. And then when we turn on the support for with arrays, then we see that in most of the test cases, we get a performance improvement. Right? The percentage of time needed to complete is less, with the exception of two benchmarks, Sunflow and Aurora. Here's the specific numbers instead of in a figure, so you can see the differences there. You'll notice the two that we lost performance in was 1.9 and 2.1% respectively. But overall, we gained, and we gained by 3.1% on average over the benchmarks. What was more interesting for us, because of the fact that we're trying to push microJIT compiling more of the bytecode, was how it actually laid out across the methods and how many more methods we could compile and how many instances of these bytecodes occurred in the benchmarks. So here's a table of the bytecode instructions. On the far axis across the top, we have the benchmarks, and along the bottom, you'll see the total number of bytecodes that we actually supported additionally by, including the support for arrays. You'll notice that Eclipse was 18,000, but in actual fact, just because you have now support for 18,000 bytecodes, doesn't mean that you're actually getting that significantly more compilation. So when we look at the actual benchmarks against the number of methods that we actually have been able to add and compile because of the array support, you'll see Eclipse had a good improvement with 25 more methods going from 555 to 580 methods we could compile. So that's how many hit the threshold. To trigger microjit, we could do it, and then later on it gets passed on to TRJIT if it hits that range. In comparison to with TRJIT versus microjit by itself, here you can see the benchmarks with the various ones down the top. So the blue is the interpreter only, which clearly has the worst performance. Next is our TRJIT by default. Okay. Next is the TRJIT with cold optimization level. Below that is the TRJIT with no optimization level. And then the bottom one is TRJIT along with microjit, where we have the array support added in for microjit. What's interesting here is that there are benchmarks where TRJIT clearly wins, because it is, once you get running long enough and the methods do get hot enough, that optimization, or that highly optimized compilation occurs, and you actually see the benefit of it because the program runs long enough. However, there are instances where effectively, by having microjit as a wedge in there, it picks up methods, compiles them quickly, gets beyond the interpreter, and then the application terminates before you get to that TRJIT to take advantage of that. So, for example, the Aurora benchmark, which is on the first column, it's 2071 for the TRJIT by default, and when we add in the microjit, we get down to 2049. So we see a slight improvement there with the microjit. Okay. It's not that benchmark. We see it in others as well, such as LuIndex, where we're at 904, where TRJIT's at 945. Okay. So the future work from this, one of them is the adaptive warm-up iteration strategies. So clearly, microjit has a benefit in some applications, but in some other applications it doesn't, because the TRJIT will hit the method, will do the optimized compilation, and it pays off in the long run. So how can we identify where we should do the microjit and where we should not in order to get best performance? We want to expand the array operations support in microjit in general. So we'd like to investigate doing operations like a new array and multi-a new array, which get a little bit more complex. And then as well, the optimization through array bound check elimination. So right now, we have to check the array bounds. If we could eliminate that, that'll effectively give us a little bit more of a performance boost at that point. So in conclusion, the scope of our work, we investigated the performance impact of adding the array bytecode support in the microjit compiler. It did show a benefit, not too surprising. We were expecting to see that. The key findings was that by adding it, reduced the execution time, and handling array bytecode boosts the Java program speed, especially in resource-constrained settings. So we are seeing some memory footprint benefits there as well. The implication is expanding the array bytecode support in microjit. It progresses Java's efficiency in limited resource environments, and it set a solid foundation for implementing more bytecodes in the templated compiler. I'll be happy to answer your questions.
Please come to the mic.
So what fraction of the Java opcode space does microjit currently cover? And how much further did this push it, and how much is left?
All right, so I'll try to remember the numbers off the top of my head, Matthew.
Ballpark is okay.
I know Shubin would know. So I believe by adding the arrays, we bumped it up by about 10%. We're still missing about, I believe, 20%, right? Some of the key ones that we're missing that's causing us to lose a lot is on the invoke static and invoke special, and those are underway. And I think with those two, they get us a really good capture, because I think right now we're seeing about 30% of the methods that we can actually compile.
Okay, thanks.
Yeah.
Thanks for the talk. I probably missed the reason why was a couple of benchmarks that slowed down. Do you think that was because like compression overhead increased, or is there any other things you think of?
The reason why we felt those benchmarks slowed down, you're talking right here?
Yes.
Yeah, is because of the fact that the methods that had arrays in them, and we JIT compiled those, we only kind of called them a few times beyond the threshold. And so we didn't run long enough to kind of outweigh the interpretation 3 or 4 more times versus compile it and execute it faster 3 or 4 times.
So it was like just only adding the compilation overhead, right?
Yeah.
Oh, okay, thank you.
Yeah. Even as a template compiler, it's going to have that pause, and you're going to consume some more time.
Hello, thank you.
Thanks.
I'd like to ask about whether your code templates for the array bytecodes use vector instructions.
Yes.
Okay.
Don't ask me to give any more details of that, but I know yes is the answer because I know Shubham struggled with them for a while. Yep.
Okay, thanks. Another question, if I may.
Sure.
Does OpenJ9 just have an x86 backend, or does it support RISC-V and other architectures?
I know it does other architectures because it does
Power,
power.
powered, of course,
And it
of
also
course,
does ARM64.
Okay,
Yep.
thanks.
Yep.
Does your JIT only support Intel though, right?
Yes, that was the initial one.
Yeah, okay.
Yeah, yeah. But there's discussion about ARM64.
Any other questions? Otherwise, we'll thank Ken again for his talk. So the next talk is entitled Hybrid Execution, Combining Ahead of Time and Just-in-Time Compilation. And Christoph Pichler from Johannes Kepler University Linz will give us the talk.
Sorry for... thanks. Just do what is written there. Okay, thanks for the introduction. I also want to emphasize that this work would not have been possible without a fantastic team. So my supervisors, Pele Lee, Roland Schatz, Hans-Peter Mössenberg, and also the feedback from colleagues. But enough about ourselves, now about you. Welcome to VML and SPLASH'. How did you get here? Maybe at some point in time you used some kind of route planner, and let's just take a look behind the scenes of such a route planner. So maybe from the server we get some kind of XML data with the different options for arrival. This might get passed by a Python script, might use a C library internally, and then for a nice web page we might use also some kind of JavaScript. So we see that our world is polyglot, and also the work I'm presenting now is part of a polyglot project. And all who attended the keynote already know the VM that rules it all, GraalVM. A short introduction for those who don't know it. It's based on the Java hotspot VM, so it takes Java bytecode. There is a really impressive and highly aggressively optimizing JIT compiler, the GraalVM JIT compiler, and languages that can compile down to Java bytecode, for example, Java, Scala, or Kotlin, can directly be used with this compiler. For all other languages, so if you want to implement your language to run on GraalVM, there is the so-called TWAFL language implementation framework, which helps you build an abstract syntax tree interpreter or bytecode interpreter very easily. And this has been done for other languages like Ruby, R, JavaScript. I'm sure I forgot a lot of important languages also. One other language runtime is GraalPython, which accepts Python code. And for C and C++, there is the LLVM runtime called Sulong. And the example I talked before lives in this scope with JavaScript, Python, and C and C++. Also, the examples I will show later live in this scope, but our research, and also what I will talk next, is Sulong. So let us concentrate on how can we actually execute C code. And without GraalVM, you just use a normal compiler such as GCC or Clang. So you have your C code. For example, the Clang compiler uses LLVMIR as an intermediate representation, which is platform independent. And then platform-specific optimizations can be done to get a binary code. And this can then be executed on a CPU. For GraalVM, the situation is a little bit different. So again, this is the GraalVM part from the previous slide with the relevant parts now, because I want to emphasize on Sulong. Again, we have our C program. We compile it. For this example, we can use Clang, and then we get LLVMIR and the binary. So it's just one command line option to also get the LLVMIR as a file, for example. And then what Sulong does is it takes this LLVMIR and produces an abstract syntax tree, and this is then forwarded to the GraalVM JIT compiler. So this is also a way how to execute C code, in this case with GraalVM. And Sulong comes with its own toolchain, which is the Sulong toolchain, creative name. And what this does is that this binary code and the LLVMIR are already shipped in one file. So if you use the Sulong toolchain Clang, you immediately get this file. And we will see later why this is very important for this research project. In difference to the GCC or to the normal Clang run, here I want to emphasize that everything above the line happens at compile time. So the Sulong toolchain can be used ahead of time to create the LLVMIR and the binary. And of course, building the abstract syntax tree and then using the GraalVM JIT compiler. Here, everything happens at runtime. So this is also an important distinction here. And this is what we call managed execution with Sulong. So if we execute C code on Sulong, of course, there's also ahead of time compilation involved to LLVMIR, but also very important, we have just-in-time compilation, and this is what we call the managed execution. As you can think, the GraalVM JIT compiler is highly aggressively optimizing, so we get a really good peak performance. And since we also live with this truffle framework, we almost automatically get the ability to run polyglot applications. So as you will see later, it's really easy to call code parts of other languages. And it's currently the default way how to execute C code. On the other hand, we have native execution. This has been possible with GraalVM if no LLVMIR is available. And for this, we just take the binary code, forward it to a foreign function interface, and then let it run on the CPU. Here we have different metrics, of course. As already said, only if no LLVMIR is available. And as you can imagine, for the managed execution, the warm-up performance is not really great because there is a lot of interpretation involved. And in contrast to this, here with the native execution, the warm-up performance is really good because all of the optimization is done already at compile time. And our approach, also in the title of the presentation and of the paper, is hybrid execution. So we try to combine those two to really get the best of both worlds. So on the one hand, we have native execution with the high warm-up performance, and we still want to get the managed execution for polyglot applications and to reach high peak performance later on. And we decided to do this on a function level. So for every function, we can decide, do we want to let this function run on the native side or on the managed side? So do we want to rely more on the ahead-of-time compilation, or do we want to use the just-in-time compilation and the ability to run polyglot applications? And now to the current state. There is no automatic decision yet, which means currently we just have to provide a file to GraalVM specifying which functions should run on the native side and which functions should run on the managed side. Of course, we do not have to list every single function, so there is the possibility of using regular expressions, for example, but it is still some restriction and limitation. On the other hand, it's possible to use both kinds of execution in one run. And one limitation, I will also talk about this later, is that it is static, which means if we start to run one C program or one program, there can be different languages involved. For example, the foo function here is always native. So currently, we don't have a possibility to, for example, after 100 iterations, move the foo function to the managed side and then execute it on the other side, so to say. So this is currently not possible, but I will mention this at the future work section again. So now to the basic implementation. And for this, I would like to start with a small example with the abstract syntax tree and the binary code. So we just have a simple C function with, or two simple C functions, foo and bar. And foo is calling bar in our case. So the abstract syntax tree might look like this, and the binary might look like this, of course, with 0 and 1 then. And now let's assume we want to run bar on the native side, so on the right part, which means if foo is already executed on the native side, we don't have to change anything. But for the left side, if the abstract syntax tree is interpreted, we want still to call bar on the native side. Therefore, we have to introduce a function pointer to point to the native side and then just link the nodes correspondingly. So we remove the call to the managed bar function and just link them. There is also the possibility that we want to execute a function on the managed side. Currently, this is only possible if we introduce a function pointer and then call the function pointer. Otherwise, we would have to modify the binary code and the source code, which is something which we didn't do. One reason for this also is the difference in the effort and the outcome, because we realized the best runtime win is, so to say, when we take leaf functions as native functions. So functions that do not call other native functions, if we move them to the native side, we have the best improvement currently. And if they call other functions, the callers of the native callers can still be native, and the performance still does not lag that much. Therefore, we just skip the other direction currently. And now back to our example in the beginning. So here we just have a JavaScript function which creates points out of text, so a small point parser, so to say, with two values x and y. Then we have a C function which takes a point and adds it to some data structure. And the overall listing is a Python program, which of course needs references to the JavaScript and to the C file, or to the LLVM file in our case. And then maybe it's a bit too small to read in the back, but what is done in a loop here, we just iterate a file line by line, and then we create a JavaScript point out of it. So the JavaScript point is stored in the Python variable here, and then passed to the LLVM code. And short recap, how does this look like with GraalVM? So we have the GraalVM JIT compiler at the bottom, and the languages at the top. And this is not the end of the presentation. There should at least be the language runtimes that appear. Yes, great. I might just hit the end button accidentally. Again, with the Sulong runtime, so we have LLVMIR binary in one file, and we can execute C functions on the native side or via the abstract syntax tree and the GraalVM JIT compiler. And what is happening now, if let us assume Graal Python gets a JavaScript point, what is then done? If the JavaScript point is accessed or written or read, then Graal Python does not do anything with the JavaScript point, but just forwards the access to the JavaScript runtime. So this is also designed such that language-specific semantics are not violated. Therefore, if an access is happening, it's always done in the corresponding language runtime. And now you also see why we cannot deal with foreign language data in C if we execute it on the native side, because there is no possibility if we are in the native execution to just invoke another language runtime immediately. This only works if we are on the managed side and if we are in the Zulong scope still. And this also leads us to a problem I want to emphasize, and for that we look into this C function here, where we take a point and add it to other data structures. So we have a C array, which points to some memory, and then we just add points when we get it in a special function. And for example, the first 2 points might just be C points, because C created them, so to say, or the Zulong runtime created them. However, it can happen that the third point might be a JavaScript point because it just came from another language. And as said before, this must be accessed in managed mode. So we have to prevent that this is accessed from the native side and have to do corresponding actions. And this is also something where memory comes into play. So of course we have a heap for the managed side and we have a heap now for the native side. And if data structures are created on the native side, they live in the native heap, and otherwise they live in the GraalVM heap. However, they might be accessed from both sides, which means we need stubs for it. So if we access them on the one hand, we need to forward the access to the other. This is a bit more complicated as it's shown here. Therefore, I will refer to the paper, or please ask me offline. Yeah, it's a bit hard to skip a memory part, although the session chair is a GC expert. But for now, you just have to live with that, unfortunately. And another problem I would like to discuss, it was not as hard to solve as with the memory examples, is the file visibility. Let us just assume we have a static variable, global count, and static in C means it is not accessible from another file. So it's kind of file private. And if we now want to access this symbol from the managed execution, we have the stub sends a request address, requests the address of this symbol to the NFI, but doesn't get a response because the NFI says this is a static symbol and I'm not allowed to tell you this address because this address has been marked as private. So for example, the workaround here was to get two different kinds of information and then combine them. On the one hand, we want to know where the library is located, and this is possible to ask, and there we get a response from the native function interface. And the second information we need is, which is also in the symbol table of the binary file, where is this symbol actually located in the library, and then we can just combine these two. So now to the evaluation. How did our work proceed? A small limitation. I said it before, it's not possible to access managed data from the native side, which means it's also really hard to know in advance if a program will correctly run. And the best experience we had is with kind of wrapper programs. So here we have a JSON Python benchmark, which means the basic library is written in C, and on top of that there is a Python wrapper. And by that we can easily see which functions will access which kind of data. And with the two benchmarks shown here, the programs did not crash, but we tried others first, and then we had the crash situation because native code accesses managed data. In this case, you see the time on the left, it's a logarithmic scale, and the x-axis are the number of iterations. And if everything is executed on the managed side, so this is the default until now for Zulong, which is the light blue line, you see that the warm-up performance is not really good, but the peak performance is the best compared to the other two runs. The red one is where we just execute all C code, which can be run native on native. So here you see the warm-up performance is better because we have less code which has to be interpreted in the beginning. However, we also have less runtime information for optimization. The JIT compiler has to do less work, and this is a win in the beginning, but then at the end you see that the performance is not as good as for the managed execution. And for the, it's called manual hybrid mode here, because we just selected the 3 functions with the longest execution time and set those 3 to native, and all others were managed. And it was nice to see that we really in between managed and native here. Of course, the long-term goal would be to be on the lower part for all iterations. So the message here is, it's not really easy to find a perfect way, but you have to change the specifications over time then, which is still future work. And another thing I would like to emphasize is, of course, we tried different benchmarks, and what we saw with the official libxml benchmarks is that the libxml benchmark has different tasks within the benchmark, and we also specified the same functions to run on native and to run on managed for every task, and the results really differed. So it makes really a huge difference about the code. So depending on how the code is written and what operations does the code do, the results are really different. So we have cases where, so this is then relative. The baseline is the managed execution of Sulong, and we have the relative slowdown, so lower is better of our hybrid mode approach. And you really see, there are some cases where our hybrid mode approach is always better, which is the red line. There are also approaches where we are always worse, and there are also approaches where our warm-up performance is better, but then the peak performance is not again. And this is only an extraction of 4 representative ones. I think in total there were more than 20, but then it's complicated to see details, of course. So to almost conclude, as said, the future work, it would be nice to not having to specify functions manually where to run them. So a more automatic decision would be nice. So we are currently working on the call graph analysis to find a heuristic how to execute a function. And also, as we saw with the UJSON benchmark, the benchmark on the left, it would be nice to switch the mode at runtime. This has 2 advantages. On the one hand, we can start with more native functions and switch to the JIT optimized functions later on. And the second advantage is, if we are close to a situation where managed data is accessed from native code, we can try to switch to managed code such that a crash is avoided. And with this, I would like to conclude. So we saw that we live in a polyglot world. We implemented an approach to mix ahead of time and just-in-time compilation for a polyglot world. We got some promising results, but we also saw that there is a lot of work still to do. And with this, I would like to thank you for your attention, and I'm now happy to receive questions.
Thanks, this is really exciting. I've got loads of questions. Here's one, right? If you're making static decisions at kind of function calling granularity, what happens to inlining? I presume that's something you can't then do with your...
This is a very good question. For this task, we disabled inlining. So for the managed only, we enabled inlining because then the numbers for managed are better. But for our hybrid mode, we had to disable inlining. If you enable inlining, it can happen. Sorry for the switch. It can happen if you want to have bar on the native side, for example. That bar is still on the managed side if it's inlined. So then, so there is no problem, so to say, but you just didn't receive the expected output.
Well, really quick, if you don't mind. Sorry, really quick. You've got these 2 domains, kind of managed and native. Can you malloc on one side and free on the other?
This is unfortunately not possible. Or it can happen, because what we implemented for the memory approach is sometimes objects have to be transferred from one to the other side. And depending on where an object is located, if there is a free call, then it's automatically forwarded to the to the correct side. Yeah, this is this is also a dangerous operation to move objects from one another, because if you want to move a JavaScript point from the managed side to a native memory, it's not possible because it's a JavaScript point.
Hi, yeah, I'm curious about how you selected the functions to be on the managed or native. So like, first of all, how many percentage was on the managed side for the evaluation, and like how did you select the functions on the managed? And like, would you think if you automate that, would that improve the performance, do you think?
For the selection, we just let it run with the managed side and the profiler and just a sampler, and then just took a look how which function does have which amount of execution time. And we usually selected the leaf functions with the highest execution time. So for most of the benchmarks, it was only less than 3 or 4%, but they had an execution time of 20 to 25%, so really high impact. For the native one in red, it was 1/3 of the functions, so it really depends.
Thank you.
I just gave Jeremy a little bit extra rope if he wants to.
Oh, thank you. This is a comment, not a question, right? It seems to me that you're saying, managed native, what should we do? This is ideal for some kind of machine learning-based search optimization.
Might look into the future into that, yeah. Okay, thanks.
All right, thank you very much.
Okay. Thank you.
The last presentation is a short talk, short paper. I just wanted to check that we have, it's an online presentation, so I want to make sure that we have them online.
Hello, can you hear us?
We can hear you, but we can't see you.
If you could turn on your camera and unmute.
Sorry, are you talking to me?
Yes, yes.
Hello, sorry. Yeah, I hear feedback from the room.
Yeah. Can you share screens as well?
Yeah, sure. Can you see it? I cannot hear anything, unfortunately. I cannot hear anything, unfortunately. Should I act assuming that everyone can see my screen?
Can you hear me now?
Yeah, I can. That's better. Yeah. Should I start?
Well. Session is to be given by Artem Pelenitsyn from Purdue University, and his talk is entitled Approximating Type Stability in the Julia JIT.
Right. Hi, everyone. Thank you for accepting this talk and this short work in progress, rather. I am working with the Julia language for some time now, so I want to share a little bit about the language itself and most importantly about type stability property that I've been working about. So I will start with a simple example that shows why this property is important in Julia. In this code, I try to sum a vector of some kind of numbers. and I leave out, so there is just a for loop that goes over the vector and, sums it. The first, the only bit that I leave out here is the initial value. So let's, I performed 2 experiments here. I replaced the question marks with the integer 0, and I ran the function with the vector of floats, and it runs in 24 microseconds. And the second experiment is that it's the same vector, but the question marks is 0, is the floating point 0 now, and it runs more than twice as fast. So there seems to be something going on with optimization, or rather something going wrong when you have this mixture of types, floats and ints getting together. So when Julia programmers hit into this kind of performance issue, they would usually call a utility called code-worn type, which prints out an intermediate representation of the compiler, and they just look, so there is a rather low-level sort of SSA-like representation. It's a long chain of assignments, basically, to some virtual registers, or called slots. And what people usually do is they try to look for the visual cues in this form of types painted in red. So every slot you will notice be typed or type inferred. And this particular method instance is type inferred for the input of type vector float. So it's important that we know what kind of input or input type we compile for. And under this assumption, we get mostly blue types. So blue means good, except for the accumulator variable is its type rather is painted in red, which means the compiler doesn't know really what it is, how to store as a float or as an int, and that's why the performance degrades. So now scaling back a little bit out of this example, the reason for this, so let me try to explain it in a couple of slides. So first is Julia, important fact, Julia is built around multiple dispatch. So every operation in Julia goes through the dispatch mechanism, which means that there is a method table for every function. So for example, the plus function has around 200 methods defined only in the base library, and there is, packages defined more. And so it will try to dispatch to the most specific or most applicable method in the library. So the crucial way to run fast in Julia is to perform devirtualization, so remove those method dispatches and try to do what we call direct calls. So some time back we wrote an UPSLA paper about how JIT operates exactly, and the way it operates is, given some concrete input types, it does some kind of runs some kind of type inference algorithm, and it tries to devirtualize as many calls as possible. And those devirtualized calls are essential for all the other possible optimizations you can think of, like inlining or unboxing. So all this is predicated on knowing an exact exact method that we will call at runtime. So we sort of come to the conclusion that this property about being able to infer a most precise type or some precise type, right, for a method call is paramount, and it enables the virtualizations and all other optimizations as well, or many other optimizations as well. So type stable methods are methods that possess this property that given concrete input types, it can the compiler should be able to infer a concrete return or precise return type. And the desired property is full devirtualization, so we have no dispatched calls at all. And these methods, the methods that are fully devirtualized, they can only call type stable APIs. So that's one of the theorems from that paper. But that's not the point of today's talk. Today, the point of my work these days is we are sort of unsatisfied by the state of the art in Julia practice. So that's what programmers do. They reach to the corn type utility, and also the TUPSLA paper also deals or based off of this intermediate representation. So our goal is to be able to reason about type stability on the source level and not go into this horrible mess of low-level instructions. So the algorithm we sort of go into, or we try to propose, is based on this observation that the naive inference that, you know, we start with a concrete type as the input and we try to carry that information to the output works in the simplest cases maybe, but any operation, as I said before, goes through the dispatch. So really, in order to be able to reason about concreteness or, you know, abstractness of the return type, you have to be able to devirtualize, or at least you have to be able to reason about what you will dispatch to. So in this case, this plus can be one of those 200 pluses defined in the standard library. So in order to be able to resolve this or have some information about the return type, you have to reason about types of inputs. And so it boils down to the whole, basically it boils down to the full problem of type inference. But type inference is already implemented in Julia, as we noted before. It acts on the intermediate representation, but nevertheless, so we don't really need to re-implement type inference. We just need to figure how to supply those concrete input types for the method that we are interested in. And this is the way we arrive at the sort of general framework that we propose here, is that if you have a method that you want to analyze type inference for, you will extract its type signature, its input type, and you will try to exhaustively enumerate all concrete type C that are subtypes of the signature. And then you run Julia's type inference for the pair method and the concrete input type. So the Julia's type inference, again, is a decision that we sometimes have to defend, but the reason here that we don't build our own type inference is that if we build our own, it will not necessarily agree with what Julia does at runtime, and we really want to be able to predict what Julia's runtime does. So we rather reuse what it has for type inference baked in. And the actual sort of hard work, heavy lifting of this work is that this rather innocently looking second step, which says, well, how do we extract all those possible concrete types of the signature of the method? So Julia has a rather rich type language for a dynamic language anyway. So we already have seen nominal types, so types like ints and floats and vectors. For those, it's easy to find subtypes of those nominal types. So for example, number has these two subtypes, and if you want a concrete type, you will have to iterate the application of subtypes. So you take subtypes, apply it to number, and then you apply it to complex, and then you apply it more and more, going down the subtype lattice. And when you hit the bottom, which means you hit a concrete type, then you can stop. And the nice property of Julia's type system or type setup is that concrete types cannot be subtypes. So you just start from some point in the subtype type lattice, and you go on, and you try to collect all the leaves basically. So this works nicely for the built-in subtypes function. It works nicely for nominal types. It has nothing. I have no idea of the structural part of the type grammar, which is unions, tuples, and so-called existential types. So we will have to extend the subtypes utility with what we call direct subtypes, which is also a bit more precise name for this utility. But still, we'll have to iterate after we do one step of subtyping. So we, for example, union of number and char. Direct subtypes of those there is number and char, and then we'll have to recursively iterate over those subtypes. So this union and tuples are rather simple examples. So I'll switch to existentials here. So existential type is a type, for example, vector here, vector t, where t less than number is an existential type that will match all possible vectors that were instantiated with number types. So for example, if you call a function that declares this type as an input with a vector of ints, it will, get called because vector of int is a subtype of this or vector of int 32, for example, is a subtype of this this existential type. So you'll notice you'll have to instantiate with all the possible subtypes of the upper bound here, the number. So T will have to enumerate it, with all possible subtypes, not just the direct subtypes. And that's a little subtlety, but we, as I mentioned before, we are anyway looking for leaves, and that means that we need to implement the all subtypes utility anyways. So that's no issue. So given a reasonably tight upper bound, we should be able to just enumerate this exhaustively. So the real challenge is comes when we don't have a concrete upper bound. So when in the methods in the Julia APIs, you would usually see just a vector input, and vector means vector t, where t from bottom to any, which is basically anything that any Julia type would suffice to match this type, right? Or vector of any Julia type will suffice to satisfy this type. So the issue in such types, there are several issues actually with them, but the simplest one is that you can recursively instantiate parametric types if you don't have a bound on parameter or any other bound on any. So you can just go into loops, start and trying to find and trying to enumerate all the possible concrete types here. So we have a couple ideas how to handle this. So first, you will notice, as usual, not all functions actually depend, or return types of not all functions depend on the inputs. For example, if you compute a length of a vector, length will always return int, no matter. So it's actually possible to call Julia's type inference with an abstract type, and it will, in some cases, for the functions that we call type constant, it will be able to return concrete types, and that's enough to handle this kind of cases. And the second idea to handle any is actually comes from this observation that we were trying to go from top to bottom, and we rather try to start from bottom, start from leaf types, and not go anywhere. So in that case, we just don't run into this issue of going into loops. Yeah, indeed, we can sample types from some input, some packages, see how we can run the tests and see what's being used, what types are used to instantiate all those methods in the test suites, and we can collect them, and we can then use them later on to enumerate possible input types. So that's what we do, and that's what we call approximation, because we can not enumerate. So by sampling, we necessarily approximate. We can't sort of exhaustively enumerate all possible input types in those cases. But our preliminary evaluation against the earlier Uppsala work shows that the numbers that we compute for type-stable methods, the amount of type-stable methods in those packages that we analyze, so there is just some 10 popular Julia packages, are actually pretty close to what we saw when we did tracing. So when we just ran tests and see if whatever test call is stable or not. So that's where I want to leave this presentation, and I'm happy to take any questions. shouldn't stop sharing the screen if there are questions about slides. Get back always.
Do we have any questions? We have one question. Thank you. Can you go back? Do you want to come up here? You want to come up here?
Yeah. Oh.
Now that we looked at all the machinery for finding concrete types, can you go back to the slide where why we needed them? I sort of like lost track of the purpose of finding all of these. So
right.
We need to find.
Yeah, that's how we.
A single concrete type or every concrete type?
So ideally, every concrete type. Yeah.
And then based
that's
on
how we,
all concrete types, you can then say that this is stable if you've seen everything.
Right, right, exactly.
Thank you. Any other questions? If not, then we will conclude the session. Thank you very much, Artem.
Thank you. Thank you.
Hello, everybody. Welcome to the last session of the VMIO workshop. We'll have 3 talks in this session. We'll also have some closing remarks from Andrea at the end, I think, I hope. The first talk will be about how to collect garbage in blockchains, and Luke is going to be the presenter.
Thank you very much, Adam. So as already said, the talk is about blockchain, and we focus on a new trend of blockchains, namely compute blockchain, general compute blockchains that can be perceived as some kind of a new virtual machine that is secure and distributed at the same time. The idea is that the computation is taken and then mirrored, replicated across different computer machines, and of course, because one cannot assume that all computer machines perform the task in a faultless way, and also there may be malicious node, there's Byzantine fault-tolerant consensus that takes place on the computation. So there are several application cases. One of, let's say, foremost cases is obviously decentralized financial exchanges, also smart contracts, decentralized autonomous organization, cloud services, but there are other applications like decentralized social media and so on. To focus on blockchain, the runtime model is a little bit different to classical computing, although one can usually program in a high-level programming language, but underneath there is a transactional execution model, meaning that a program that is deployed on a blockchain runs a series of transactions underneath, and the transaction is nothing else than a sequence of deterministic program operations or program instructions. Determinism is important, such that the distributed compute nodes can reach consensus in a repetitive way. A transaction itself has access on the program's main memory, and that main memory is persisted on the blockchain, meaning that a transaction somehow transitions the memory image from one version to the other. Of course, at the implementation level, there can be optimizations. For example, there can be differential memory image snapshots being taken. Also, like modern blockchains are able to truncate the memory image history in a secure way, so there's no need to retain the whole history to replay that from the beginning. Our focus is a little bit even more specific. We focus on the internet computer, which is one of these general purpose compute blockchains that uses WebAssembly as the virtual machine, so the common denominator for various programming languages that can be executed, can be used as platform for that blockchain. Of course, the set of features is restricted to deterministic features, meaning that, for example, and that matters here in that talk, no parallelism, and we also do not use multi-threading for the programs. Currently, the standard of WebAssembly, although there's a proposal for 64-bit, is on 32-bit. That means that the standard model for programs executing is that they have a main memory with 4 gigabytes. There's separate memory, but I don't discuss that yet. It's out of the focus for that talk. For the internet computer, there's also fairly new programming language called Motoko. That's a language that is specifically designed to ideally fit the concepts of the blockchain. Of course, there's also support for other programming languages. Motoko itself compiles to WebAssembly. From the language model, it's very similar to TypeScript. The Camel has been specifically designed in order that there's high resemblance and easy start for programmers that want to work on that. It's object-oriented, imperative, functional, asynchronous, and what matters for this talk, it's memory safe and therefore also garbage collector, meaning it uses an automatic garbage collector to reclaim memory. When we look at garbage collection, there are a little bit specific requirements when it comes to a blockchain. One of the aspects, I guess the most important one, is incrementality, namely that these transactions that I mentioned, they impose a very strict limit on the amount of computation that can be done. That's for different reasons. That's one of the reasons it's that these consensus can take place and these memory images, the logical memory images can be taken. And that's implemented by having an instruction limit. That's a very hard limit. Whenever computation takes longer than this limit, sometimes also called gas, then the computation is canceled and the effects are rolled back. So it's important that garbage collection work must fit into these transactions. So a simple approach of just having a stop the world garbage collect is infeasible because maybe the memory complexity is higher than could fit in a single transaction. It's also not possible just to span the transaction work to the next transaction because there's always mutator work in every transaction. Mutator work is actually what triggers these transactions. There's another aspect which I think matters on the blockchain, namely the longevity of the programs. Programs that are deployed once on the blockchain conceptually live perpetually, so they have infinite lifetime. Doesn't mean that they are always executing code. They can be more passive there. Sometimes there are again interactions with the program, but that means that memory management should more specifically also look at avoiding fragmentation problems, because if there are fragmentation problems, they would persist and would stay there for a long time. There's no way of healing them by restarting the program or something like that. So that's why we designed a specific garbage collector for Motoko. It's an incremental garbage collector. The idea is it's very much inspired by the Java Shenandoah's garbage collector, I guess one of the more modern garbage collectors. It has snapshot at the beginning, incremental marking, the evacuation compaction phase, and uses Brooks forwarding pointers to do its work. However, it has certain differences that comes to these specific requirements. One is that the old GC phases are unbounded, which isn't the case in these more classical mainstream incremental garbage collectors. On traditional computers, you may afford to have certain phases that have not like a bounded phase. Typical such phases are, for example, scanning scanning the root stack. There's an extra updating phase, which I explain later on why we have that. And of course, the performance model is a little bit different. It is tuned towards the blockchain cost model. From the implementation perspective, the garbage collector work is the increment. The GC increments are interleaved in a deterministic way. Of course, at the end of the transactions, we also keep the liberty to move them within the transactions, just as to mention that the very start of a GC run and the end of a GC run, that's what we require to happen at the end of the transaction. Of course, the increment have to have a strict number of instructions as bounding limits in order that they can fit into the transactions. And there's a specific aspect in the WebAssembly, technical aspect, that we don't have access to the native call stack for scanning the root pointers or patching pointers that we may need to update during moving of the objects. That's why we can use, in our case, it's not that problematic, because at the end of a transaction, the call stack is empty anyways. That's why we have chosen this implementation design. There are alternative design possibilities too. As usual with this evacuation compaction garbage collector, it's based on a partition heap by fixed sized partitions for 4 GB address space. We currently have 32 megabyte partitions, and simple because it's single threaded. As I mentioned before, a single bump allocator for regular sized object is working. We have special handling for large sized objects. When the garbage collector starts, the first phase is the marking phase. It's full heap scanning to deal with any cyclic garbage, even inter-partition cyclic garbage. It's a conservative marking phase using snapshot at the beginning, deletion barriers. That means whenever there's a write barrier, whenever we overwrite a pointer, then the overwritten, the old pointer is taken into account for marking. New allocations are marked. And as mentioned, the design of the garbage collector just requires for that phase that when it starts, the call stack is empty, and that's actually one of these critical phases that are often unbounded in classical garbage collector. That's how we solve it very simply by just not having to do that due to the runtime model. By the way, we just use conservative marking as the idea because that allows us, once it has started with an empty call stack, we can even continue with pointers present on the call stack. So if we want to have more fine-grained interleaving with the mutator, this would allow us to continue even to switch into the next phase, the evacuation phase, even if the call stack is not empty. The second phase, also fully incremental, is evacuation phase. There we have the freedom to focus on partitions. We can select partitions that we think are worth to compact by moving out the live objects that have been marked into new partitions, fresh partitions. And we do that in a very conservative way. We actually move all partitions that have at least a certain very low threshold of garbage. And if memory is scarce, meaning because that's copying, like it's a copying garbage collection process, and if we have not enough space, then we focus on just the the highest garbage partitions in order that the evacuation phase does not exceed the memory, the free memory that is around. During that phase, as mentioned, it's also incremental, meaning that the mutator may continue to access, like to traverse pointers, look at pointers, and they may lead, of course, to old locations, and this is no problem here because due to these forwarding pointer techniques, every object that has a forwarding pointer in its header, meaning when an object has forwarded, it can be atomically redirected by just adjusting this forwarding pointer to the new location. The downside is, of course, that every load or store or even object referential equality comparisons involve indirections. In our case, that's quite cheap in that sense. We also implemented like the classical way of having conditional load burials, which proved due to this synthetic cost model of the blockchain to be more expensive, as we measured something like 27%. Once that phase is done, we have an extra phase, the updating phase, that actually scans through the whole memory and patches all pointers in the sense that no forwarding is anymore in use, so that all pointers lead to the most recent evacuated locations. And we terminate that phase by having, again, a call stack that is empty. That's also important, that we don't miss any like pointers that we can't scan. The reason for this separate phase is that typically garbage collectors leave that phase out and just combine it and piggyback it on the next marking phase. So when the GC schedules again, then during the next marking phase, this updating can just take place at the same time. But however, then we have this delay just to wait for the next scheduled GC round, and that may be a long time here on the blockchain. And also because we use conservative marking, that it's even more problematic because a new object allocation during the GC run have to retain at least this full GC run. So this proved to be have much faster reclamation. Measured some experimental results by having our own benchmark, compared it to classical but production garbage collectors that we also have for Motoko, copying garbage collector, two-space garbage collector, a threading, compacting garbage collector, and two-generational garbage collector. This shows the GC pause limits for these 4 garbage collectors. The red line actually just shows the limit that we intended to have, and of course for the incremental garbage collector we can configure it that it exactly matches these limits. The counting is a little bit different. The garbage collector internally it counts steps, not instructions, but we can linearly map these steps to instructions. The other garbage collectors have, for certain cases, have substantial longer GC pauses because the GC work is not limited to a fixed number. Also, comparing performance is a little bit different when it comes to runtime performance, because in the cost model, there's this counting of instructions of the synthetic model, and this was not expected to be the case, but luckily we were lucky to reach that. The incremental garbage collector is not more expensive. It's even a little bit cheaper than the traditional garbage collector. This shows the average cost of running a program, mutated cost plus garbage collection cost. The reason for that is that for the incremental garbage collector, we have this liberty on focusing on partitions to evacuate. We don't need to do the full garbage collection job, but somehow can limit to what it's to the most beneficial aspect. Of course, then the GC throughput is similarly related. The incremental, it's as usual, like it's with a trade-off, comes with a trade-off. The footprint of the memory that is allocated, this shows the maximum size the program has ever grown to. It may still be that the memory is reclaimed, that some free partitions are around, but this is a little bit higher for the incremental garbage collector. That is expected. It's because of the forwarding pointers that are in place. We also do not always evacuate all partitions. Partitions with very low amount of garbage stick around, so that also accounts for that memory. And of course, if we compare it to compacting garbage collectors, this is higher because we need this extra copying space to be there. But we can limit that, but this is usual trade-off. Scalability, that was actually the reason for that, because on the blockchain we have like large-scale applications. People want to exploit the 4 gigabyte address space nowadays. They also plan to move now beyond 32-bit. And we see here this was taking the same benchmark, but only taking the cases where we can scale allocations. And we see here that it's possible to allocate way more objects with the incremental garbage collector, because in the classical garbage collector, we always hit this instruction limit first, because at some point there are too many objects, or the heap is too fine granular, or the space to be copied is too much, such that the GC work in total exceeds this transaction limit, and then it fails, and then programmers would have the trouble that it doesn't scale beyond. So to wrap up, I guess garbage collection on a blockchain is a specific niche that has different requirements to the classical, classical garbage collection. The emphasis on incrementality is much higher. It has really these strict limits, really similar to real-time garbage collectors in the sense that one needs to fit it into these transaction limits. Another aspect which I think is important, that compaction is relevant, because fragmentation would stick around with this conceptually indefinite runtimes of blockchain programs. Also, performance is a little bit different to be tuned to. Maybe design choices that were good choices in a traditional computer perform a little bit differently on a blockchain. That's, for example, the forwarding pointer techniques works well. Another aspect is that we use mark bitmaps, which is typically avoided, but mark bitmaps somehow lower the amount of dirty page access and then help us to limit the memory image sizes, differential memory image sizes that the system takes. And to conclude, the Motoko incremental garbage collector has been specifically designed for this requirement, for these requirements. So thank you for attending the talk, and I'm very happy to take questions.
Okay, cool stuff. Happy to see this. One question, so you had this like number of 15% barrier for garbage to evacuate. Mm-hmm. Where's that number coming from? I would actually have expected a higher number. Or
mm-hmm. It's usually higher as far as, if I'm not mistaken, in the Shannon-Dar garbage collector, it's much higher. It's like 60%, if I'm not mistaken. But I haven't looked at the recent code. But here it's like we measured what is somehow, with regard to like this performance table, what is somehow, like we didn't fit it immediately to that, but we didn't want to go further for the allocated memory to be there, because allocated memory is an additional cost factor on the blockchain. That's one of those aspects we considered.
That makes sense. Okay.
But it can be tuned, like we were discussing that internally. So.
Right. Okay. Thank you.
In the beginning, you said that you store the memory image in the transaction, or did I get that right?
Actually, the transaction is the transition function. Like there's a memory image, then transition computation takes place. Computation is really like code that runs on this memory, on the main memory, but somehow the blockchain, when the transition has completed, then that state is decided. This is like a true state that is kept like for continuing computation, or rolled back if there's something problematic about that or exceeded some limits. And then there's a new memory state that sticks around for that program. And so. Okay.
So the memory image, is it the whole memory
state? Conceptually it's the whole memory, but technically it's a differential memory. That's why we are keen on having not like too many dirty pages. I just showed the logical perspective, because like this memory state is a little bit different on blockchain than traditional. And there's also like what people typically like, which can cause confusion, is it truncates history, so there's really a need of doing garbage collection. Otherwise, the latest program memory image would continuously grow. When the program has additional allocations, then the allocated space always grows. You can never reclaim memory, and then these images like would monotonously grow, and garbage collection also helps in that regard. And history can be truncated, and it's really like reclaiming memory in total.
Last chance for a last question. All right, let's thank the speaker again. And while the next speaker is setting up, we'll have one of the workshop co-organizers say a few words. Stefan.
Hello, everyone. I'm here for the steering committee. I basically just want to slightly interrupt because I won't be here for the last talk, and thank Andrea for organizing. So, round of applause. Of course, also, thank you very much to the session chairs. And of course, all the authors and everybody who submitted the paper. This workshop is really for you guys. And to make it happen next year SPLASH is going to be in Pasadena, so LA. We are always looking for an organizer. So if you want to volunteer, please come to me. And you could be involved in the organization if you like to. That also goes to the kind of senior PhD students who want to look behind the scenes, and we will pair you up with a more experienced person to actually get a workshop like that organized. So again, Andrea, thank you very much for all the work, and hopefully one of you is organizing next year.
And of course, let's thank Stefano, because without him, not much would have happened, this workshop. Next talk will be by Juan Fumero. I was thinking of how to squeeze in a one-sentence summary of his talk, but I realized that that is not possible, so I'm just going to let him start talking.
Okay, good. Thank you, Adam. So, hi, my name is Juan. I'm a postdoc at the University of Manchester. Also, I'm an Intel innovator. And today I'm going to show you the project we're building for the couple of past 2 years with Intel. It's called Beehive SPV Toolkit. This is, in a sense, it's a toolkit meant to be used by a compiler, by that JIT compiler or static compiler. We use it in the context of JIT compilation for binary code generation, okay? For GPUs, FPGAs, etc. The thing about this library is that it's also automatically generated. You might wonder why you want to do this. Okay, stay to my talk. I will tell you why. So, I'm going to motivate why we do this, and then I'm going to show you a bit of background, okay, some terminology that I need. We are working in the context of Java, okay, automatically offloading code to run on GPUs, FPGAs, to accelerate workloads. So I need some to set up some terminology. And then I'm going to explain to you the basic components or the main components of this toolkit. Later, what we did was to integrate this toolkit that you can have as a separate tool for your stuff. We integrated into the Tornado VM project. I will explain what it is if you haven't heard about that before. Okay, so let's get started. Why do we do this? So we initiated a collaboration with Intel, and the goal was to improve the Tornado VM ecosystem, the Tornado VM technology for the OneAPI software ecosystem. So OneAPI is a new toolkit from Intel that has many things, many libraries inside, and it has also new libraries for accessing accelerators. The thing about this OneAPI is that some of the libraries are accessible only through SPV. SPV is an intermediate representation, okay, standard portable representation in binary format to run on accelerators. So in Tornado, we need access to SPV in binary format. So we thought, okay, this is complicated because it's not easy to generate. I mean, most of you have worked on compilers before. It's not easy to generate binary directly, right? So what we decided was to decouple the optimization process from the actual code gen. And the code gen is a standalone library, okay? And that's the part of the work that I'm going to present today. Right, so let's set up some terminology. OpenCL. OpenCL is called Open Computing Language. It's a standard, it's a programming model and standard for accessing accelerators, okay? FPGAs, RISC-V accelerators, AI, GPUs. Any vendor that implements the standard, okay, you can use that implementation to run your workloads. OpenCL has two parts. It's called the host code. It's the pure runtime. Let's say, allocate that buffer on the GPU. Run this kernel. That's the host code. And then it has another part, which is device code. The device code is the function that runs on the GPU, on the FPGA. And you can express with OpenCL that function in kind of C-like, okay? It's an extension of C. Or, recently, you can have SPV. SPV is in binary. Obviously, you are not going to tell the developer the problem in binary. This is meant to be used by an optimizing compiler, okay? What's the benefit of SPV? Well, one of the reasons is that many companies provide these kernels, and they don't want others to see that code. You can disassembly, but it's hard to read that code. Another reason to have SPV is that because it's very low level, compilation time goes down, okay? So we target SPV. One more thing about this ecosystem. So we target also in the OneAPI ecosystem from Intel. OneAPI it's a bit confusing from Intel because they have the specification, which is open, and the tool or the implementation, which is also called OneAPI. Okay, but I'm referring here as a specification. It has many components, has a few compilers, libraries. You have libraries for deep learning, AI, acceleration of math operations, linear algebra, etc. What we are interested in is the low-level library. It's called Level 0. That's a quite close library to OpenCL, if you like. The thing is, to run Level 0 applications, you need SPV, okay? And that's what everything comes into place. Right, I hope that makes sense. And you can say, well, what's the deal? What's the gap here? Well, we have Tornado. Imagine you have a Java application that wants to use an accelerator through SPV. Now, how do we currently access SPV? Well, as it is right now, you can have your OpenCL program and then call an external tool like LLVM to go through, from OpenCL down to SPV. So it's kind of weird, right? Because then we have to do a sub-process to call LLVM, it's totally decoupled, etc. No. Then another alternative is to have like a SQL program. SQL is another standard, well, many terminology here, but the key message is that this solution is based on C, C++, but we want Java or any other managed runtime programming language, okay? So what we want to achieve is the following. You have a Java workload, and you want to accelerate part of that Java workload on accelerators. Here is represented Intel HD graphics, Intel discrete GPUs, you can have NVIDIA GPUs, etc., etc., etc. So for the first part, we do this toolkit. So that's part of the talk that I'm going to show you today. So the toolkit is in this step. It's in between the Java application and the actual code that we generate. And then for the whole view, we use the toolkit in order to go from Java down to the actual hardware. We execute the code, right? One thing is to be able to generate code, and then we have to execute the code. To execute, we need this low-level API called Level 0. And I'm going to show you today these two tools. I'm going to focus mainly on the toolkit, but I'm going to show you how we perform with the Tornado VM at the end of the presentation. So let's talk about the toolkit. The toolkit has three components. It has the library generator, the actual library, and then a client. Now, I'm going to go to the question. Remember that I said at the beginning, the actual toolkit is also generated. Why? Because what we did was, SPV is a standard, okay? It's defined by Kronos. Kronos is a consortium of many companies, Google, Intel, NVIDIA, et cetera, They agree on the specification for the intermediate representation, and they put a file in JSON format for the grammar. Today is SPV 1.2. Tomorrow is 1.3. Next year will be 1.4. So what do? We take the JSON grammar file. We have our toolkit to generate automatically a library. So for the next releases, hopefully, it's just a matter of milliseconds, right? Or a few seconds. Exactly, you got the point. So for the library toolkit, let's focus now step by step. So for the library, we use two open source software. We use, to parse the JSON file, we use an application, well, a framework called Jackson Annotation Library. And for the actual generation of the library, we use the Apache FreeMaker. So what's the goal? With one framework, what we did was to annotate, okay, based on the JSON structure file. And we get back the list of SPV instructions, SPV operands, and SPV kinds, if you like, data types. So once we have those lists in memory, what we do is to use the FreeMaker library to, one by one, just generate Java code for those instructions and those operands. At the end of the process, you have a full library in a jar file format ready to be consumed by a customer, by a client. So just to give you a little bit more in detail, here I represent on the top left the high-level overview of that JSON format, okay? The JSON is divided for the SPV specification. So we have two main components. The one that expands into more entries are in blue, while the gray ones are like a terminal operations, right? If you like. So the SPV grammar is divided into main blocks, instructions and operands, and then for each instruction we have a DOP code, the capabilities of that instruction, and so on and so forth, and something similar for the operands and the kinds. So the first type is with the FreeMaker framework. We say, let's parse the whole grammar file. And then we say, okay, the file is dividing into the magic number, a list of instructions, and a list of operands, and whatever we can have in there. So once this is done, we have in these two arrays, SPV instructions and the SPV operands, all the instructions and operands that we have in the SPV specification, all of it. And then we continue the process, and with the templates that we also have, you can think about the template like a Java-ish, okay, Java with a lot of typical template programming. And then we fill those. So we have templates for instructions, and then we have templates for operands and kinds. At the end of the process, we have the whole library ready to be consumed. So let's talk about the library, how the library looks like, because we say it's functional and it's composable. Well, that's what I believe. The thing is, if you know what to generate, that's the key part. You have to know. But if you know what to generate, it's very easy to compose, to build SPV module. So let's say SPV module, the standard tells you, start with a header that has the magic number, a version, a bound, and a schema. So we say, in Java, because we do code generation from Java, okay, it's a Java library. We say, SPV module, build the header with the major, minor version, the loop bound, the ID bound, and the magic number. And that's done, okay? We continue generating in the library side with all these instructions, and when we close the module, it's already stored in binary, right? Let me give you another example. So the SPV has capabilities. You can have, for example, if my module, my kernel on the GPU uses FP64, I have to enable as a capability. So it's as easy as I add in the module a new capability, and I add, for example, in this case it's IN64, but you can have FP64. Or I add this module is going to be a kernel. Kernel means for compute, not for graphics. Okay? We're using, by the way, we're using the GPU for compute, for acceleration of workloads, not for graphics. SPV is a common representation for both compute and graphics. While we focus on compute and we have the library open source, that means, and we cover the whole spec, that means that someone, if you want to, you can have Vulkan applications running with Java. That's very cool. We haven't explored that, so we focus on compute for now. Okay, just to give you a flavor of another example, more useful example, let's say we want to cover this structure if-else, okay, from the OpenCL side, how will it look like when you program the library with the library. So you have an ID, SPV is an SSA representation, and we use in our compiler GRAL SSA, so it's a perfect match. So we say, give me a new ID, it's gonna be for the comparison, then I have to add an instruction called operation I equal, it's an integer, it's an integer. Then we build the instruction, and then we build the branch. The thing is, you don't have to remember all of this. You go to the standard, and the order of the operands and the type of operands is exactly the same as the standard will tell you, okay? And that's a good thing. That's what I'm saying, that if you know what to generate, it's easy to build it. In fact, the way we did it was to use LLVM underneath, okay? We have our OpenCL, we know what to generate from OpenCL side. we make use of that LVM and say, this is structure that I want to achieve. Okay, this instruction, this instruction, this instruction. So we build our compilers with all these libraries. Right, and then we have the client application. So as I say, it's open source, you can download it, and as a standalone, you can disassembly SPV vinyl, but nothing special about it. It's just, for us, it was an example of how to use it from the client side. Right, so how do we test this? So we integrate this into Tornado VM. What's Tornado VM? Tornado VM is a parallel programming model, okay, a parallel programming framework for offloading a subset of Java to run on accelerators, okay, GPUs, and etc. And for the SPV part, we took the library, okay, as a code gen. Right, so Tornado VM, even though it has a VM in it, it's not a VM by itself, okay? So it needs an existing JDK. In fact, the reason why I call it VM is because it's a nested VM, okay? So you have your Java application, and Tornado VM is a kind of in-between, right? We call it VM because Tornado manages memory, manages compilation for you, manages execution for you, et cetera, et cetera. But it doesn't run by its own. It runs with a standard, with OpenJDK-based distributions. OpenJDK, we can also run with GraalVM, Corretto, et cetera, et cetera. And we don't compete with Java. So the main goal of Tornado is to complement what Java cannot achieve by itself, okay? So we want to run on accelerators, but we don't want to access directly to accelerators. That's the key part. Right, so what we did was, okay, Tornado VM has a few backends already. We had one for OpenCL, one for CUDA, PTX, it's assembly code for CUDA, and then we add a new one for SPV with this library I was talking about. So, yeah, let me jump to this one. So what we did was to have directly the full JIT process, the full JIT compilation pipeline, right? So to integrate this Java library, we also need the optimizer. And the optimizer is an extension of the Graal JIT compiler. We use Graal as a library, right? So we extend Graal with a lot of phases, new nodes in the IR to be able to generate GPU, FPGA code. So in Tornado, I'm not going to go into much detail, but essentially there are many compilation phases. We have what we call a common IR. It's already Tornado IR. You can think about Tornado IR like a superset of the Graal IR, okay? We have more information. For example, we know if a loop is parallel, we remove the loop, for loop, and we say this is a parallel loop with a range, for example, things like that. We know it's a reduction, so we know how to perform a reduction in parallel, things like that. Then that's what we call a common IR, and then we start specializing. So the IR will look different depending on the backend you choose. If you choose CUDA, we will look different. If you choose OpenCL, it will look different, and so on and so forth. And at the end of the process, at the end of the JIT process, the optimizer process, because we combine Graal optimization with Tornado optimizations. For example, we call the parse escape analysis, okay? That's Graal. And then we combine with, at the very low tier, we combine with FMA expressions, so fast multiply add operations that very fast on these devices, by the way. Right. Once the code is optimized, we introduce the library I was talking about for the pure code gen to generate SPV binaries. Okay, so I'm not gonna go into the details here. I'm gonna jump directly into the evaluation. So what do we do here? So first, we evaluate the code generation itself. Okay. We have a set of benchmarks. Each block, let's say, is group represent a benchmark. And in that benchmark, there are two versions. One for OpenCL, the one we already had in OpenCL, in Tornado VM, and the new one, SPV. And we have, for each bar, let's say, we're dividing into two. What we call the code generation is the black portion of it, and the driver compilation. The code gen is the actual build module with the library that I was talking about, the SPV toolkit. The yellow part, the driver compilation, is the JIT part. So SPV and OpenCL, you can think about both of them intermediate code. Then you go to the driver, you send this to the driver, the GPU driver, and the driver will do the final compilation, okay? And that's the time that is represented in yellow here. So Let's analyze the black portions. The black portions are and the Y scale, the Y axis represents pure runtime, so the lower the better, okay? In nanoseconds, this is in nanoseconds. So as we can see, the code gen takes a bit of more time, okay, with SPV compared to OpenCL. Why is this? Because we have to build the SPV module with all these, objects and so on. So it's easier to understand or to reason about, but we have more pressure on the Java itself because we are allocating a lot of objects, etc., etc. Right. Then we go to the driver compilation. So once the SPV module is generated, then we compile to get the final module. And we see that it's around 4 times faster, 3.9 times faster, that part of the compilation. That makes sense. That's what we wanted to get, right? And overall, if we speed up the compilation process by 2.7x, which is great. Okay, this is the benchmark for pure code gen. But what about end-to-end time? How have we improved something? Well, now my baseline is Tornado VM running on the same GPU. It's an Intel GPU, by the way, I didn't mention before. The baseline is the Tornado VM running all these applications on the Intel integrated graphics. And I'm showing here speed up, so the higher the better, okay? So, as we can see, in most cases, running on the same GPU, but going from different driver or from different implementation, in this case is PV, you can get extra performance. There are a couple of reasons for this. So, first of all, the number of threads that are deployed on this hardware are quite likely different between the two implementations. So, even though we are running on the same hardware, the number of threads we deploy is different. Why is this? Because in OpenCL, in Tornado VM, we have an heuristic. The heuristic, we took it from the NVIDIA guidelines. And as you can see, it's an heuristic, okay? Actually, it's a very long subject of study in academia about how is the best number of threads to deploy, right? In level 0, we go through the level 0 heuristics. So the number of threads we deploy is different. What does it mean? Well, I can deploy 1,000 threads, but depending on your block, if you organize 32 by 32 or 64 by 64, you can get different performance. In some cases, we deploy the same number of threads, but the performance was different. That's the case of the blue filter, by the way. The blue filter was deployed exactly the same number of threads. Okay, that application is computational photography. It's a filter for you blur part of the image. And going through SPV with level 0 can give you more than 2x performance on the same device compared to OpenCL. But in general, it should be roughly the same. And what we see that in the average time, SPV is slightly faster, but kind of it's 2% faster than level 0. All right, so to conclude, I show you here. First part was a toolkit. The toolkit was automatically generated to adapt to new versions of the standard as we progress. And then we took that toolkit to integrate it into the Tornado VM project to be able to actually generate and optimize Java code to be able to run on SPV devices. And the final key message is that we can speed up the overall process of execution, not just compilation, but execution by 50% in some cases. And with that, I conclude my presentation, and I'm happy to take questions. Thank you very much.
Yeah. On your runtime graph, I was very confused by the axis. So it's listed in nanoseconds, but then you have like 2 to the 8 nanosecond. So is your essentially compile time like 1/10 of a second?
Yeah. Oh okay. That's taken from our profiling. Our profiling takes everything in nanoseconds, so I dump everything there. Yes.
Okay.
It's a few milliseconds. Yeah, I should put it in milliseconds. Yes. Sorry.
Okay.
Yeah, you're right. Yeah. Yeah, Tornado has a default profiler you can enable, and by default it's nanoseconds because it's a more reliable unit from the GPU profiler. We take that from the GPU driver directly, and this is nanoseconds. Yeah. More questions?
There was one benchmark that had a significant regression. Did you look into it? Do you have a sense of what was going
the
on?
number, yes, that's the case I was mentioned that the number of threads are mismatched. It doesn't, so, okay, just to clarify, number of threads is the same, okay, because number of threads matches input size usually on GPUs. Block of threads, how you organize those threads on the GPU is different. Let's say I run 1,024 threads by organizing 32 blocks of threads, or 64, or 128. That can, on GPUs, believe me, this is a difference, right, in performance, and that's one of those, yes. In fact, what we see in general, just to tell you, so we see that level 0 get a better estimation of the number of threads compared to our heuristic in OpenCL for integrated GPUs. We plug in for a proof of concept. Tornado can run also on the new ARC GPUs, the discrete GPUs. OpenCL is way better. Our heuristic is way better than the level 0 ones. Yeah.
So is this a situation where the main difference is not actually, is just the heuristic? Can you copy the heuristic?
Yeah, yes, we try that. It's not that easy though. So, yes, it's easy, but we are not going to see the same performance because we are going through the level 0 stack, software stack with the driver, etc., and the OpenCL stack, okay? So it's not exactly the same. So, yeah.
Definitely time for one more question.
Hello, thanks for an interesting talk. I know for conventional CPU instruction sets, there are formal specification languages like SAIL. I don't know if you've seen SAIL for ARM CPUs. And I wondered whether the JSON file you take as input to describe your SPLASH'23 instructions and so on, whether that is kind of the basis of some kind of formal specification, and whether you're leveraging any of that infrastructure, you're just kind of parsing a text file and doing the stuff.
Yeah.
That we normally
Well,
do.
I don't know for the CPU, for the GPU. Well, I didn't go to the details. You can in the papers we have more details. So it's not just as straightforward as just parsing the JSON, putting the templates. We also introduce some utility methods for easy generation of code, like mainly factory methods, right? To be able to generate that code. So I don't think it's just as easy as taking that JSON and magically it's going to work. No. I'm not claiming that.
Okay.
But
So
what I claim is for similar programming models, like OpenCL, for example, could work, okay, in the same way SPV can work here.
What gives you the confidence, Juan, that your code generator is correct?
Great question.
Yes, that's what I'm asking.
Great question. So we had that in discussion in the paper. SPV, the LLVM toolkit, has an SPV validator, SPV val, and we go through the SPV validation, okay, and everything is correct. If there is a minimal amount of something that is not correct, I'm not talking about the instruction in the wrong place, I'm talking the semantically not correct, it breaks. For us, the whole unit test suite plus the whole bench is passing completely with no errors. That gives us an extra confidence, yes. Plus, we also have our own validator in the toolkit, and we discovered some like kind of cycle dependencies between instructions. We raised this exception, this issue to the standard. Basically, we check if the compatibility is correct. So I can't remember the details, but it was something like, if you want to use this SPV capability, that works with compute and FP, whatever instruction. We discovered that we want to use one capability, and we say, but that's not valid in SPV format. But any driver was telling us that was raising deception. Right? I raised this to the Intel community, to the Intel guys, and they say, okay, that looks like an error in the standard. I don't know if I didn't follow up, but yeah. We have an extra validation here. Yeah. Thanks.
Yes. Oops. I wanted to say if there's more questions, I'm sure Juan is going to be happy to answer them after the talk. I think I broke it. Hopefully not too bad. No, it just fell off. The last talk of this session is going to be given by Quentin Ducasse, and this is going to be about how to test new hardware extensions, new hardware features when you're developing JITs. I hope.
Yeah, thank you for the introduction. So, my name is Quentin Ducasse. I'm from the ENSA Bretagne in France. So this is joint work with my PhD advisors, so Pascal Cotteret and Loïc Lagadec. And I'll present to you JIG, which is a JIT code binary generator for hardware testing. So what does it mean? I'll first go into some context and background. So I'm sure most of you are familiar with VMs, so I won't dive in this figure that I believe is maybe incomplete. But one thing that I would like to highlight is that the JIT code region is a key component because it is both performance critical in the sense that it has optimized machine code, and it's also security critical because it's usually a part of memory that has to handle both writable and executable memory. And as you might know, this is usually a bad sign of vulnerability that you can be vulnerable to code injection attacks, code reuse attacks, and so on and so forth. So there is a history of attacks. So I mentioned code injection, there's also code reuse. We can also attack some of the VM internals. For example, even if you have secured your JIT code region, you might just give it as input malicious bytecode that will just generate malicious machine code in VM. So I would just like to highlight 3 state-of-the-art defenses that I think are very interesting. So first one is called JIT Guard, which uses Intel SGX, which is now deprecated, but which is a secure enclave that has encrypted content that is decrypted on the fly. So this is to accelerate and protect the JIT compiler. Then we have Nojitsu, which uses intra-process isolation with memory protection keys. So they manage to handle some of the permission checks in the user space and accelerate while keeping security guarantees. And the last one, which dates from last year, which is called CITIS, uses Intel CET, which is a control flow enforcement technique that stores a shadow stack somewhere in memory, and that also performs indirect branch tracking. So what I want to highlight with these 3 papers, which I believe are very good reads, is that there is a definite need for hardware-enforced security due to the performance it manages to squeeze out for performance-critical components. So now that this is the context of why we might need some hardware features, I'd like to give some background on the Faro VM, which is our mental model for the design of JIG. So Faro VM uses an indirect thread interpreter, a linear non-optimizing method-based JIT compiler that we recently ported to RISC-V. And usually what we have is the VM source code that's written in a restricted Smalltalk that we had a talk earlier on. So that's called slang. That we then transpile to C, and we generate the executable on which we can execute the application. We also have a test framework in which we managed to do black box testing of the JIT compile code using a CPU emulator, which is named Unicorn, and I will go back on this more later on. And so I tried to motivate why we would need hardware security features, and now I'd like to motivate why the RISC-V ISA might be a good candidate for that. So if you haven't heard about it, it revolves on 3 main objectives. First one being open source, in the sense that the standards that are open for everyone. You can still modify and do a proposal for instruction groups that are still being drafted. It's also modular, so you have instruction groups that are separated to support a wide range of applications. So as an example, we have the base one, which is I for integers. We have multiplication, and so on and so forth. And if you manage to design a core that supports the RV64, IMA, FDC extensions, this means that you're ready to support the fully featured OS such as Linux. We also have several standard allocated spaces for extensions. What does that mean is that there are dedicated opcodes, so that are named custom 0 to 3, that are fixed in the standards and that won't be used by future extensions. So this means that any change that you might want to make now will be available in the future and will not overlap with another instruction group. We also have some hints, which are instructions with specific arguments that fall back to being an op if they are not implemented. So for example, here the LUI x0 and value is usually the load upper immediate, so you would take the 20 upper bits of the value and load it in the register. If you pass it the register x0, which is the hardwired 0, this will do nothing, but you can implement some logic in your processor to actually do something. So I talked about why we might need custom instruction, but which custom instruction I'll be talking about. So the first example, which I call E1, are simple rotation instructions that are not actually fixed in the RISC-V standards. So they are very basic rotation instructions that you might expect. The second one is the use of a shadow stack. So you can just put 2 new instructions, CFI call, that you would put right before a call to store the return address in some part of your shadow stack, and CFI return, where you'd have to pop the return address and compare it to your actual return address to see if the control flow has been disrupted or not. And the third one is duplicates all memory accesses and tags them with a domain. So this means that, for example, we can use it to put in the JIT method, the JIT code region could only use duplicated memory accesses that are tied to a domain and that can only access the data in the JIT region. We also put some specific change domain and rated domain instruction that allow the switching of this actual domain to be performed. So, some motivation design of JIG. So, in the team, we are mostly hardware developers, and when we would like to make JIT-specific extension, JIT-specific custom instruction, this means that we have to support the whole software stack. And as RISC-V is still unstable, we'd like to get something way more simple and flatten the stack to get a meaningful representation of what might be the JIT code region. So we do some assumptions. First, that the JIT and ahead-of-time compilers are the only components that are modifying machine code, and then that a snapshot of the JIT code region is representative of the changes that are made by those components. So this means that if we manage to get the JIT code region after a certain amount of time, we might say that if we get this one, it's representative of the application that's running. So our motivation is to flatten the software stack significantly so we can speed up hardware development and support VM-specific custom instructions. So JIG, which is the French for jitter in signal processing. So it's a workload generator. It's a random workload generator that will produce an executable file modeled after the JIT code region and support custom instructions ready to execute on extended cores. So we designed it around 3 main ideas: parameterization, so it takes in-input qualification parameters to qualify diverse application and VMs. It's modular in the sense that we'd like to extend it with custom instruction, we'd like to extend it with custom JIT code region constructs, and it does heavy use of testing, so we have lots of sanity checks, and we have a custom execution model to validate the binary we generate before running it on the real or simulated hardware design. So the 3 main components are very simple. There are methods that are filled with random instructions and calls. We have a model for polymorphic inline caches, which is basically a number of caches and then our methods. And we have some trampolines to manage the call to and for the interpretation loop. So our binary structure, which is self-contained, is we have an interpretation loop, that calls all JIT elements in a random order. Then we have each JIT element that will call a number of other elements, and both have access to the different trampolines for routines. The resulting binary is compiled using the binary framework provided by the RISC-V assembly tests. So this means that it will automatically be supported by the different RISC-V core that support this assembly test suite. So for parameters, I will go quickly over them. Basically, they are split into what qualifies your VM, what qualifies your application. And we would say that for a VM, we have a JIT code region size that we fix, the frequency of the different JIT elements, so methods and inline caches, the different usable registers that we might need, so we control the environment of our generated binary. And then for the application, have number of methods, the difference we might want to inject in the method size variation, the call occupation, and we can also, and the one I think is interesting, is the frequency of instructions. So if we want to have a binary that's very memory intensive, we can change that. And also we can specify the shape and size of the data. So the binary generation works using two components. One is a generator, which is responsible for the higher level structure handling, and a builder, which is just responsible for instruction emission. So it goes as follows. First, we'll instantiate the trampolines. Then we determine the method base size using the fixed JIT size and the number of methods. And then we'll instantiate the different elements, but all inside the same API. So we just go through the different weights that we provided for them and instantiate them. Then we'll fill them with a random instruction following the distribution that we chose. We'll patch calls, so the call graph is fixed at binary generation. Then we'll generate data and link it in a self-contained binary. So as the generated binaries contains random instruction, we have to perform some kind of sanity checks. So the registers that are used are fixed at generation. We sanitize jumps and branches so that they don't break the call graph. Data accesses are indirect through dedicated base registers, and we perform the call patching when the whole call graph has been fixed. And one thing that we wanted to enforce is that the binary execution is correct. So we extended it with testing, which I will just come to. So modularity and the test framework. So if I come back to the three examples that I presented earlier, so to include the different instructions in the JIG framework. So for the first one, we've added the instructions in the random generation of immediate instructions and register instructions. And I would argue that this adds, 100 lines of code. Most of them are boilerplate code, and that's why I just written on the side 12 lines of code. So this means adding them to the random generation and simply in the correct place in the code. So this means overloading the builder, random I, and random R generation. For CFI call and CFI read, so the shadow stack custom instructions, they are added to the method call epilogues, so right after the return, and they are added at call generation. And same thing, it adds 2 instructions, and I'd argue that this adds 12 efficient line of code. For the last one, so we added 15 instructions, and we completely replaced the random generation of stores and loads. When we also changed the method epilogues in code generation so that we check and sanitize the domain that we're jumping to. So for this one, we add a bunch more lines of code, but once again, I would argue that this is basically 54 lines of code. So the test framework we define is based on Unicorn, which is a lightweight wrapper on top of QEMU. It defines flexible wrappers that are triggered in events such as exceptions, memory accesses, or register values that are being reached. We extend them to catch custom instructions as defined in the standard. So this provides an easy API for the user to add a custom instruction that will have an effect in the software test. So for the rotation, what we do is when we catch the rotation, we'll simply perform the rotation on the result of the 2 registers, push it back in the unicorn state, and resume the execution. For the example 2, we'd store a list with the return address on the software side, and just push and pop to and from it. And for the third one, we add a tag of domains to duplicate instructions, and we ensure that we're in the correct domain when we're executing, and fall back to the traditional load and store. So I will just show you a set of use case that we've used JIG for. So the hardware development stack that we have to go through to extend our core with custom instruction looks like this. So this is without having to put a VM on top. So first we have our core definition, so our processor implementation that's written in a high-level hardware description language, which is called Chisel, which is an extension of Scala. Then we compile this Chisel language description of the core down to Verilog code, system Verilog code, sorry, which is another hardware description language that I have to use. And then once we have this, we have the choice to either go through the synthesis tool to get down to the bitstream and put it on an FPGA, or go through a simulator, a cycle-accurate simulator, which is what we do. So we can execute the JIG binary on this very little simulator. So it is able to run a fully featured OS, but it's extremely, extremely slow, and we cannot go through it to validate that. So that's why we like to have a binary that models this JIT code interaction and give us some insights on whether our custom instruction is suitable for a JIT compiler or not at all. So as an example, we took some values from the Faro VM dumps and artificially extended them to generate different application classes. So, can you see my mouse? Yeah. So on the left, we made a varying call occupation. So what that means is if a method in the JIT code contains loads of calls or not. And on the right, we use varying memory accesses. So this is on a core that simply implements the E1, so the rotations. And we wanted to see if we can artificially inflate the number of application classes that we have, so we can have a meaningful workload to work on. So, as a conclusion, I presented JIG, which is a workload generator for hardware testing. I believe that it's parameterizable to qualify VMs and applications. It's modular, so we simplified the addition of elements and instructions and provided a way to test your custom instruction before adding them in the actual hardware. We are implementing variants of E2, so the shadow stack, and E3 in an actual core. And we'd like to compare them because usually when we have a paper presenting a shadow stack, they will compare to the software version, and usually they're faster. And the same thing for the example number 3. We like to have a common ground to compare different solutions and to provide insight on what would be an interesting fit for a JIT compiler. And yeah, and the Faro VM already supports the E1, so which is just a rotation, but it supports it in its custom testing environment. And the final step that we would like to reach is to have a complete stack running, which means the core implementing custom instructions that might be interesting and that we can propagate through the VM and running on top of an OS. But we're still far from there, and this is just a way to flatten the stack and try to have some preliminary results. So thank you for listening to me. The code is available open source on GitHub, and I actually have some questions to you. So, which custom instruction would you integrate in your VM JIT code? What does it mean for you to integrate custom instructions? And also, which parameters would you qualify the JIT code for your VM? So I have much more details in the paper on how we use the parameters to generate binary, to have a representation of this piece of memory. But I'd be happy to hear your thoughts. Thank you.
So this is going to be probably the first talk when, if you come to the mic, you can either ask a question or provide a response. So please go ahead.
So you were mentioning 3 different extensions or sets of instructions that you were adding, and you were saying they were based around security, and the second and third, I definitely see that, but how is a rotation a security primitive? I didn't quite get that.
Oh, no. The first one is just an example of a very simple one that we can extend. It's definitely not a security one, sorry. Yeah, maybe.
Okay, so everything made sense for me with the one exception, which is
I didn't understand the random generation thing. Because if you have a JIT and like you just want to extract an executable subset of that, why don't you just grab like lots of them from a real JIT workload and take those and then feed them into your core? Like I didn't quite understand the random part.
Yeah.
Could you like explain that again?
Yeah, of course. So we made that choice because actually it was easier to control the environment on this subset of, how to say, we would just qualify the dump of a Faro VM, so after running some kind of application, and then we can get some metrics on the used instructions, on the number of polymorphic inline caches in comparison to the methods, and then we try to artificially expand that on something that we can control a bit better. So which is, we control the registers a bit better on this
So
side.
it's almost like a fuzzing like approach, except you're trying to mimic the
yeah,
you're trying
exactly.
to match statistically the like number of load, store, compare.
Exactly.
things. Okay.
It was a bit, how would I say, faster for us to do this way. It by no means replaced the actual JIT compilation.
Okay, that makes more sense.
Yeah, thank you.
Any more questions? If not, let us thank Quentin one more time. And I thank you all for coming to this session, and Andrea will have some closing words for the entire workshop.
Okay, so I will be actually quite brief. Just want to thank you all for your participation. One aim of the workshop, which is also something that the program committee evaluates when deciding whether accepting or rejecting a submission, is whether the submission has potential somehow to stimulate good discussion at the workshop. I hope that you enjoyed the workshop and that you liked the discussion that was arising here. I would like to thank Adam and also Tony Osking for having chaired sessions of the MIL 2023. And earlier, Adam thanked Stefan, and this is something that I would like, even though Stefan is not here, I would like to remark that is really the reason why we're having the workshop and the mind behind. So it's really Stefan that should deserve your thanks and not me. So even though Stefan is not here, maybe we can thank him one more time, because it's really up to him if we are here today. So thanks, Stefan, virtually. And yeah, and thanks again. I will be around the whole week if you want to talk or exchange some discussion. And yeah, hope to see you around. Thank you very much.